Right. Good afternoon again. Welcome. Sorry for the technical issue that we faced. Let's get started again. So today we'll be having the first session of the microcontroller-based embedded system design course. Today we'll give a brief introduction to the course. This is the lineup that we have for today. We'll first have a keynote speech by our guest speaker today, and then our head of the department, Dr. Ranga Rodrigo, will be addressing the gathering. We'll then go into details about the course introduction, what we will be covering throughout the 16 days, and we'll give some information about the course logistics as well. So I'll be covering that part. My name is Subodha. I'm a senior lecturer with the Department of Electronic and Telecom Engineering, and I'll be the course coordinator as well for this particular course. We'll also allocate you some time for the Q&A session. You can clarify any doubts that you may have, and then to wrap everything up, we'll be giving an introduction to microcontrollers that will be done by Mr. Abarajithan. So let me introduce our keynote speaker for today. She's a graduate from the same department, Electronic and Telecom Engineering, Dr. Hasantha Malavipathirana. She's now a postdoctoral researcher. She got her PhD from the Florida International University in the US. She's also a proud recipient of the 2020-2021 Cadence Women in Technology Scholarship. Prior to starting her PhD, she was an application engineer at Synopsys and also served as a junior lecturer at TNTC. So we are glad to have her join with us. We are happy that she accepted the invitation to deliver the keynote speech. So without taking any further, Dr. Hasantha Malavipathirana, I would like to welcome you to deliver the keynote speech.
Thank you, Dr. Subodha, for the nice introduction. And thank you very much for the invitation. I'm really glad to see this number of participants and this kind of a wonderful course starting. I'm really happy to be a part of it. Thank you for the introduction and the invitation.
I'll stop sharing so that you can share your screen.
Thank you. Could you please make me a co-host or sharing options?
Should be able to share now. Let me.
Okay. Yeah, okay. Yes. Can you see my screen?
Yes, we can, and we can hear you clearly as well.
Okay. Thank you. So today I will be talking a bit about embedded system design, mainly focusing on applications and opportunities. My name is Hasantha Malavipathirana. So to start a little bit about myself, as Dr. Subodha mentioned, I graduated with a PhD from Florida International University just a couple of weeks ago. And my research area is designing analog integrated circuits for scientific computing and array processing applications. So can you hear me?
Yeah, we can hear you. I think one person is having an issue. Hopefully he will get it sorted.
Okay, thank you. Yeah, so as he mentioned, I graduated from ENTC back in 2016 and worked as an application engineer at Synopsys. So this picture is I'm working in the lab. So this green board is kind of an embedded system. I'll come to that later in this talk. So before starting talking about embedded system, let's see what happened with the computing technologies over the time. As you know, before 1950s, during 1940s, 1930s, we had computing was a big deal. There were huge computers, sometimes room-sized computers, as you can see from this left figure. Computers were like this is a control room for an old computer. But with technology scaling and everything, computing became more usable and it became accessible to many. After those huge computers, then we have personal computers. Started with IBM personal computers, and then now we have laptop computers, and high performing desktop computers. And those are general purpose computers. Then now today we have mobile phones. Computing is enabled even in mobile phones, tablet computers, or these iPhones and Samsung and all these state-of-the-art mobile phones. They have very huge performance. And now computing is also enabled in edge devices, even in wearable devices and smart home devices. So the computing is pushed towards every device that you find at your home, in medical devices and everywhere. So with this, there's a huge potential for embedded systems to enable computing in these node and edge devices. Yeah, so to talk a bit about the applications of embedded systems, they find use applications in many domains, including consumer electronics, such as cameras, smart appliances, wearable devices, and then comes to communication devices, such as cell phones, routers, modems, and networking devices, and also in automation and control, such as in automobiles, robotics, UAVs, and even space rovers. So there are embedded systems in most of all of these appliances, and even in instrumentation, such as lab equipment, scientific equipments, and medical devices. So these images show some of the applications, even in such as in an ATM, we find embedded devices, then smartwatches, automobiles, including GPS, and smart thermostat, smart doorbells, paying tap and pay payment gateways. So we find embedded devices everywhere. And here are some more examples where we find embedded devices such as the smart home devices, Google Home and Apple Home. They have a lot of equipment, including smart speakers, doorbells, smart security cameras, Wi-Fi, smart plug, thermostat, so many devices. So inside a embedded system, what are the main components? So I'll give you an example with Apple Watch 7. So this is a dissected image of Apple Watch 7. So it has a controller. In this case, it's S1 64-bit processor. This is a microprocessor-based embedded system. So it has a processor and a small battery, and then sensors and actuators devices. And the right side figure is another example. So this is a less sophisticated smartwatch. This is actually a fitness tracker, Fit with Charge. It has a microcontroller as the main controller. So that's STM32L1 microcontroller, and a battery, a display, and other sensors and actuators. Actually, note that this microcontroller STM32L means this is an ultra low power microcontroller. So that comes to another important feature in embedded systems. So most of these systems are battery powered. That means these devices when you are designing an embedded system, we need to be aware of the power consumption and how we manage power in the system. So this using low power components is an important feature in embedded systems. So this is a block diagram showing an embedded system. So the main components are a processing unit, in this case a microcontroller, and then you can there are firmware and software related to the processing unit. You can program the processor, and then we have input devices such as sensors. So this is showing a couple of sensors such as ultrasonic sensors or altimeters, temperature sensors, and we use analog to digital. So these sensors capture physical changes in the physical environment. So those are analog signals. Then we use analog to digital converters to convert that signal into a digital signal and then process using the processing unit. Then we use, again, digital to analog converters to convert the digital signal into an analog signal back again, and then give it to the actuators or the output devices, such as displays, motors, speakers, and even smart bulbs. So other than that, in an embedded system, we have to communicate between these input-output devices and the control units. So for that, there are several communication protocols that can be used. So I'm showing two of them, two simple serial communication protocols. One is I2C. So that is a two-wire protocol using a serial data bus and a clock. And the other one is a serial to peripheral interface. That's also a serial communication method. And other than that, there are read-only memory and both static and dynamic memory associated with the embedded system and some other peripheral components. So when we talk about embedded system, one of the main components is the microcontroller. So there are different kinds of microcontrollers available in the market, such as from Microchip, ARM, Atmel, Atmega, and then we have boards like evaluation boards such as Arduino with the microcontroller connected to other peripheral devices. And inside a microcontroller, there are main components such as the control processing unit, memory, a clock generator, ADCs, and analog to digital converters and digital to analog converters, and I/O drivers, input-output drivers. Here are some of the DIY projects that I came across from the internet that we can easily do with embedded microcontroller-based systems. This one is a floor cleaning robot. Actually, this employs Arduino Uno board and some couple of motors and motor controllers. So this kind of a product is actually like, it has a potential for a product. It's actually this floor cleaning robots are sold for between $100 to $200 in the market. And another example is a basement flood detector. It also employs a simple components such as an Arduino and several sensors. Another thing is we can design our own smartwatch using a couple of components. And so that then moving on to the next section, when we talk about microcontrollers and microcontroller-based systems, the first step in designing a microcontroller-based system is for this schematic design. So at first, we have to identify the specifications of the design we are going to make. For example, if you are designing an embedded system based on a particular microcontroller, say STM32 microcontroller, then first we have to figure out the specifications, read the data sheets, and figure out the specifications. What are the required power supply, oscillators, clock modules. So figure out the specifications first, and then go into designing a block diagram, and then we can move on to the schematic design. So in this case, I'm showing a reference schematic, a microcontroller-based design for the STM32F4 microcontroller. In this case, so this is the microcontroller, and it has supporting other supporting components such as the programmer and debug part using a JTAG programmer, and then we have to we have to set up the oscillator and the clock circuit, and then there's a power supply, and then we have to connect the other peripheral components, such as the other sensors or the actuators that we intend to use. So for circuit for this schematic design, we can use circuit design, circuit editing and simulation software, such as Altium Circuit Maker, Multisim, or Proteus. And so once we design the circuit, we can perform simulations to see the functionality of the circuit and verify the functionality. And once we've verified the functionality, we can go into a layout design. So this image shows the layout of an Arduino-based microcontroller. So this one is the schematic for a microcontroller-based design for Atmega chip. So yes, this part with the most number of pins is the Atmega footprint for the chip, Atmega microcontroller, and then we have a part for the clock, and then there are some layout. This section is for the voltage regulators. So in a circuit, we use voltage regulators to maintain a stable voltage for the microcontroller. And these wires are the routing. So I think you will do one of these designs for your own by the end of this course. So that will be exciting. And once you design the PCB and fabricate it, we have to choose the components, and the next step is soldering and assembly of the components. So for PCB design, we can use electronic design automation. These are the EDA tools. So these are the tools that we use for schematic design and PCB design. So we can use tools such as KiCad or Altium or Eagle for PCB design. And so here from this, I'm taking a small detour. So I showed you the schematic design and layout design of an example design for a microcontroller-based system. And now I'm taking a small detour, taking you to a case study example of an embedded system that I used to test an analog computing chip. So that is based on my research. So to start, let's see what is the difference between analog and digital signals. So in all this electronic equipment, what we are doing is we take some input from the physical environment, process it, and then take an output based on the processed signal. So these information carrying signals can be either analog or digital. So for example, the signal produced by a sensor. So we use physical quantities such as, for example, in a temperature sensor, the sensor produces an electrical signal corresponding to the physical environment. So that electrical signal is an analog signal. It's varying. It is continuously varying with time, and it has a continuous value, continuous amplitude. So these analog circuits are the circuits that directly perform on these analog signals, for example, such as sensors, amplifiers, and filters. Then we convert this analog signal into a digital signal. The most commonly used digital signal is the binary 0-1 representation. And we use this 1-0 representation in logic gates, multiplexers, microcontrollers, microprocessors. So all these are digital circuits. We use this 0-1 representation. So the process of converting an analog signal to digital is done using mixed signal circuits. We use analog to digital converter A to D to convert an analog signal to a digital domain. And then in the microcontroller, we do the processing as a digital signal and then again convert it to analog using digital to analog converters. So this is the procedure in a normal microcontroller-based or microprocessor or any digital system. So instead of doing this, we try to explore whether can we do the processing in analog itself. Instead of using these A to D converters, can we introduce processors that are analog? So the control itself is analog. So we perform the computations and processing in analog. So this idea is not new. It actually computing was analog back in 1950s. So, but it was superseded by digital computers because digital is very robust. It's robust to errors and it's easy to program, scalable. So that's why we have digital computers. But we are trying to, again, going back to analog, we are trying to study whether can we use analog circuits, because now we have advanced transistor technologies rather than back in 1950s. So we are trying to use these advanced technologies for analog circuits and try to see whether we can use these analog circuits to perform the computations. So that is an emerging research area. So to give you a clear example, consider a physical system such as a spring mass system. So in this kind of system, we can model this physical system using set of equations. To be precise, differential equations. These are like partial differential equations and ordinary differential equations. So these differential equations can be mapped directly to electrical signals, and these equations can be mapped can be directly represented using an electrical system that uses components such as integrators and analog voltage-based additions, voltage or current-based additions. So this is kind of an analog computing system, and I must say that analog computing is not going to replace digital computing, but what we are trying to do is try to solve particular problems such as this kind of differential equations using analog systems, because differential equations are inherently continuous time and they are analog, so they are a good candidate for analog computing systems. So this image is a test setup, and I would say it's kind of an embedded system for testing an analog chip. So this is the analog chip. It's an analog computing chip that solves a particular equation. This chip is solving a partial differential equation to model sound wave propagation. So this is the green board I was holding in the first picture. So this board is it's a PCB. So this chip we call it an analog core processor. So this chip is actually a slave device, and the master device in this system is a computer. So the host computer programs this chip using an serial to peripheral interface. So we have a SPI connector in this board, and this SPI is controlled using a microcontroller. And then the board has other peripheral components such as op-chip amplifiers, and also it has a power supply and power regulator network on the chip, on the PCB board. And this we are using an external signal generator or external supply. We can provide an input signal to this analog chip, and the outputs are and then it produce analog outputs. and those outputs are converted using digital to analog to digital converters into digital domain for comparison and results post-processing. That's a different part. So I wanted to show you this figure because it's kind of an embedded system that we use to test the chip. So actually, also I wanted to show you this figure because this is the bare die and these tiny wires. So this is the chip when you look it under a microscope. So when you look at a microcontroller, if you take a microcontroller, you will see that the chip is actually a black package. So this kind of this is what you see inside that black package. So there's a bare die, and it has several pads, and these tiny wires are called these can be aluminum or gold wires. And they are connected to the PCB. This process is called wire bonding. So even in a chip, even in an Atmega microcontroller that you take, that with inside that black package, there's a chip wire bonded onto the package. So this this is the schematic of the PCB I showed you. So we have a footprint, we have a space for the analog die, and then there are some voltage regulators to provide the correct power supply to different parts of the board. And this is the schematic for SPI buffer, and we have some pin headers, and then we have some decoupling capacitors connected to voltage regulators. So that is to reduce the supply voltage noise. And then we have some outside external amplifiers to amplify the analog signal coming out from this chip. And these are the footprints for the RF radio frequency connectors on the PCB. So once we have all these components connected in the schematic, we can go on to PCB layout. So this is the layout of that board. So this part is the layout, the regulators. This is a 4-layer PCB. It means the screen part is the ground plane. The maroon color is the power plane. And then red and blue route wires are the signal routing. So they carry voltage and current signals. So this is showing the pin header for the SPI, and this the yellow area is for the analog chip. So that is the layout, and this layout, and we have a footprint for the amplifiers, and these tiny things are capacitors, and there are resistors and capacitors. So all these are surface mount SMD components in this chip, in this board. And the PCB was designed using Altium Designer. And here's the close-up of the chip. So this is the analog chip, and the bottom left figure is the image of the chip under a microscope, and the top left is the layout of the chip. So actually, similar to a layout of a PCB, we can lay out a chip. So actually, the chip comes before fabricating a chip. What is inside is a layout. So this layout consists of transistors, and this the outer area consists of pads. So these pads are for connecting input-output pins and power supply, power and ground connections. So this is the equation I mentioned. I will not go into all the mathematical details. So this equation is solving sound wave propagation inside a jet engine nozzle. So this is a partial differential equation of two variables, sound density of a sound flow, and u is the velocity of sound flow. So use in that analog IC, we are solving this partial differential equation. So to starting with the partial differential equation, we have to map it into analog circuits. So to do that, we use an algorithm called continuous time delay approximation algorithm. So the main point is we start with the partial differential equation and convert it to voltage signals so that it can be mapped using analog circuits. This is the basic schematic block of the analog IC I mentioned. So it as a op-amp based circuit. So this is a op-amp based summing and scaling circuit actually. So if you input several voltage signals, this circuit can add scale and add those in voltage signals. So here's another part of the schematic of the IC I showed. Actually, it is like 1/20th of the chip. So we interconnect this kind of 15 of this kind of circuits to build the layout I showed earlier. So going a little inside, so each of these operational amplifiers I showed these rectangles. So they are made of transistors. So this is one of the main difference between analog and digital ICs. So in digital IC design, these microcontrollers, microprocessors, they are based on logic gates, AND gates, NOR gates. So there are transistors inside the gates, but we focus on logic gate based design in digital ICs. But in analog ICs, we directly work with transistor level designs. So this is a transistor design of the operational amplifier I showed. So it has a couple of like 50 transistors. And this op-amp is working at, it has a gain bandwidth product or unity gain frequency of 600 megahertz. And here's the layout of the op-amp. So actually like similar to a printed circuit board, we can lay out the chip. So this is the layout, part of the layout of the chip. This was done using 180 nanometer CMOS technology. And actually these tiny blue lines, they represent the gate of a this blue line is actually a gate of a transistor. So that is a polysilicon gate. So all these blue lines, they represent transistors. So once you have a circuit and the layout done in a software, so this layout was done in Cadence Virtuoso using Cadence Virtuoso software. You can also perform circuit simulations and see whether we get the required outputs. So these are some simulation results from the circuits for the two variables we were computing, velocity and density, and also from measurements of the chip, we can obtain this kind of results. So I will not explain what it is. So I just wanted to show you that we can fabricate a chip, mount it on a printed circuit board and perform testing. That is also similar to an embedded system. So there are some other applications of analog computing. One of the main candidates is for AI and machine learning. So in machine learning, you may be familiar that there are a lot of matrix vector multiplications and multiply accumulate operations. So usually they are done in a GPU or in a normal general purpose computer. But to perform multiply accumulate operations, we can analog circuits can do it in an efficient way, just using voltages and currents. For example, this is called a device using a device called memristor. If we can simply use Ohm's law and Kirchhoff's laws to add to sum and to add several to perform additions and multiplications of currents and voltage signals, and then obtain multiply accumulate operations. So these kind of circuits could be they could be energy efficient and fast. So this is an emerging research field. People are looking into using this kind of analog AI accelerators, mostly with embedded and edge computing devices, because these are energy efficient. Now, I took a detour into explaining some analog computing techniques. Now, again, coming back to the main topic, embedded systems. So, as we discussed, with the advances in technology, embedded systems are emerging in every field with smart devices and the Internet of Things. So there are devices, smart devices such as home automation devices, or medical and health monitoring devices. There are smart devices everywhere, and these are connected using the internet, forming the Internet of Things, and we can control smart devices at home, even though you are not at home. Irrespective of the location, we can control these devices, and this is an emerging field. So there's a huge potential for Internet of Things devices and smart devices, especially these devices enable machine learning and artificial intelligence. So some of the machine learning and learning can be done offline in a cloud-based system, and the smart devices then gives you collect data and perform the required functionalities. So with all these technologies and applications, a huge emerging field. So there's a really good opportunities for embedded designers in this domain. And some of the main players are like in global players, even including Apple and Google in embedded systems. And the local opportunities include companies like Son 24/7 and Aptinex. So there are really good opportunities for embedded designers. So that concludes my talk. So in conclusion, we discussed about the applications of embedded system. They find applications in many domains, including consumer electronics, security, and medical appliances. And embedded systems allow home and industry automation. There are smart devices, wearable devices, IoT. So they are emerging applications for embedded devices. Microcontroller-based embedded systems involve designing hardware, software, and firmware. And there are multiple opportunities in this embedded systems domain for the emerging engineers. So that concludes my talk. Thank you for listening. And thank you for organizing this wonderful session. I hope you all the best.
Thank you, Dr. Hasantha. Really appreciate your insights and your knowledge in this area. So I think that everybody who took part in the session got a very good overview of what the domain looks like, the difference between analog and digital, especially. And then in a while, we'll be discussing what we will cover in the course. So this is a very good introduction and a good segue into what we have planned for today and for the rest of the course as well. So thank you again.
Thank you.
I think it's very late in the night for you. So I appreciate
Yes.
like it's, I don't even know. I'm guessing it's around 4:30 if you're evening this course.
3:30.
3:30, yeah. Thank you very much for being flexible with your time. This is the time convenient for the students. So I appreciate you being and joining at this time.
Yeah, thank you. Thank you very much for the invitation. I really appreciate it, and I'm really happy to help and help the students. And this is a really good initiative to motivate the students and teach them the state-of-the-art technologies and help them move forward with the world. So again, like, hats off.
Thank you. I appreciate it. By the way, does anybody have any questions to ask from Dr. Hasantha before we let her go and get some sleep? We can give a couple of minutes. Dr. Hasantha, we have Dr. Rodrigo also joining with us.
Hello, sir.
Dr. Hasantha.
that sounds a bit weird.
Right, so I think we did not see anything coming in. If something comes up, we'll try to answer on behalf of you. If we are unable, we will forward that to you, and then we'll get back to the student.
Sure.
Thank you again.
I'm happy to have. Thank you so much, and wish you all the best with the rest of the session. I'll be off then to get some sleep. Thank you so much.
Right, thank you.
Thank you, Dr. Hasantha. Have a good evening. Not evening. Have a good
Thank
morning. Very soon.
Yeah, thank you. Bye-bye.
Bye-bye.
Bye. Right. With that, let's move on to the second part of today's session. And as I mentioned earlier, it'll be an address by our head of the department, Dr. Rodrigo. Dr. Rodrigo is currently serving as the head of the Department of Electronic and Telecom Engineering at the University of Moratuwa. And he was a huge supporter of the courses that we are developing. So he will outline the motivation and the reasons behind those as well. He's also a graduate from the same department, and he mainly works on computer vision. That is the same area he did his PhD. He got his PhD from the Western University of Canada. So without delaying any further, Dr. Ranga Rodrigo, I'll hand it over to you.
Yeah, thank you, Dr. Charles. Please enable me to share the screen. I have a few things to do, not too many.
Sure. I think it's enabled.
You see?
I made you a co-host as well, so it should work now.
Yeah. Thanks. Thank you very much, Dr. Charles, for inviting me to briefly talk to the people who are joining for this microcontroller-based embedded systems design course. Actually, no one introduced Dr. Charles. Actually, Dr. Charles himself is a graduate from our department. And Dr. Charles, after graduation, he joined University of Florida in the US. Actually, Dr. Hasantha Malavipathirana and Dr. Charles lived in the same state. So he definitely knows what time it is in Florida. So he just showed that he doesn't know the time. He really knew the time, actually. Also, I tried to wear a green tie, Dr. Charles. It's light green. I think it qualifies as green, Dr. Charles. You are wearing a green T-shirt, and the banner and everything have been designed in green. Yes, so it qualifies. Yes, thank you very much. With a light note like that, I want to briefly talk about the department and why we do this course. So you can see some of the pictures of our department in the slides, and you can see that so many great things are done in the department. We are very excited about those things. You can see the airplanes that we make, the robots that we make, and the different fun activities that we do, and so on in the department. So much excitement in the department when the students are there, especially after the COVID period. We are once again having all the students in the department. So I want to talk to you what a university is about, and then talk about why this program is important to us, and hopefully it will be important and beneficial to you also. So when we think about it, a university is a place where intelligent people gather to share knowledge, to create knowledge, and to preserve knowledge. So preserving knowledge is through our lecture notes, our videos, and in the minds of our lecturers and graduates. We preserve knowledge. And then creating knowledge means we do research and we generate new knowledge. So you heard in the second the detour that Dr. Malavipathirana took, she spoke about the computations that she did in the analog domain. So people would usually do them in digital domain, but she did her work in analog domain. That's a research contribution that is new knowledge. The world did not know about it before she discovered that. So that's research, and this course is not for research though. And sharing knowledge means we teach in our university, And through this course, we teach you. So the knowledge that we have, we share with you. So this is a main pillar or one of the main purposes of the university. So that's why we want to create this program and share the knowledge with you. So, but you can see there is a financial component in everything. We have to charge some money. Otherwise, we will not be able to pay the lecturers and pay the people who are assisting to do this course. Although seemingly easy, you see, it is not easy to generate all the material and create a course like that and deliver it. So people are joining from different countries. So we can see Mr. Abarajithan, Mr. Kithmin, and so on are joining. Kithmin is in British Columbia. I think it must also be very late night there. We have gathered these people to share our knowledge with you, so that you also can get started with this very, very exciting field of embedded systems engineering. Dr. Hasantha Malavipathirana took you through a very beautiful journey, starting from the very basics, how circuits are designed, how PCBs are designed. When you take an IC, what is inside this IC, what is a microcontroller, and what are the things that you can do yourself with the microcontrollers and so on. So through this course, with our sharing of knowledge, you would also be able to start with small examples and then slowly build up your work to do complicated examples. Now for this, we have facilities in the department and knowledge. So to just briefly talk to you about the department, we take 100 electronic students. Of course, you know that from A-levels mathematics stream, you have to get extremely high marks to join University of Moratuwa. Even within the University of Moratuwa, you have to in semester 1 right now get the highest marks to join our electronics program or the biomedical program. So we have many staff members, about 20 with PhDs, like Dr. Charles and I. We are our highest degree is the PhD degree. Dr. Malavipathirana is also like that. So we have this beautiful building, and we have many laboratory classes, and many of our students get classes, and we have 2 taught master's programs. That means we teach in these master's programs, MSc in Telecom and MSc in Electronic and Automation. Actually, Dr. Charles is the person who's in charge of this MSc in Electronic and Automation course also. And we have 2-year research-based MPhil degrees, and of course the PhD degrees in the department. Now, there have been many success stories. So starting from 2009, we won the IEEE Extreme Programming Competition, 700 teams from 40 countries. So you can see the people who won this one. And then quickly coming to years close by. So in 2021, we won the World Championship in the IEEE Signal Processing Cup, and then the World Championship in this ICAs, and then we publish in topmost conferences in the world. So as a result, you can see we are a fully fledged department which has all the teaching components, the knowledge components, and the ability to share knowledge. So you can see we do this with a lot of staff members. The Chancellor himself is a staff member. So you can see a picture of me also, and then a picture of Dr. Charles, who will be handling this course. Okay, so these are places where our staff members have obtained their degrees, mainly from North America, Canada, and the United States. Then Europe, then Japan, Australia, and so on. Okay, yeah. So in the department, dear friends, we have many tracks. So one of the tracks is electronic and telecom, biomedical, robotics, computer vision and pattern recognition, reconfigurable hardware, and embedded system are these different tracks. Now, in this course, we are taking a part of the embedded systems track and make it understandable by you without assuming any electronic background, and we are giving it to you so that you also can get started with this exciting world of embedded systems design. So I will briefly talk about the electronics track, how a student would progress to the electronic track, so that you understand that so many things are there to learn if you want to obtain a fully fledged degree like in our department. So initially, maybe they will do in semester 2 a digital alarm clock, for example. Then maybe in semester 3, they will start designing a little robot like that. Maybe you also would be able to design robots like this after taking the course that Dr. Charles would conduct for you. And then maybe a programmable color to light frequency converter. So you can see the printed circuit boards that they have designed actually. So then this is a curved line sensor array robot. So you can see the beautiful PCBs that they designed, and then EMG acquisition device. So this myography, you can see from muscles, you can extract signals. So that's a circuit and then the signal that they have acquired. And then This is a fully surface mounted device micro mouse. These things run and do maybe maze solving, and then advanced electronic projects like dry contact SEMG sensor for controlling a bionic hand, like that. So actually, you can see Mr. Kritmin Vikramasinghe's picture is here. Actually, Mr. Kritmin Vikramasinghe will also join in teaching you, and he's joined tonight. Mr. Kritmin, I have gotten your permission, I guess, to have this picture in this.
So thank you so much for including all these.
Yes. Yeah. So that's one of the tracks, and then we have telecom. Then we have in that also we do so many things. In biomedical engineering, we do electronic design that are applicable for biomedical work. Then exciting things in robotics design, different kinds of robots, and they are very exciting. And some of those are flying robots. They are called UAV, so unmanned aerial vehicles. I show you some pictures, and there is this. We popularly known as machine learning track. We are very strong in that area. So we call it the pattern recognition track. So many things are there. So with this, our students are able to obtain internships, work, and go to universities in Sri Lanka and elsewhere in the world. So here are some exciting videos of the projects that our students have done. So you can see this jumping robot supervised by Dr. Peshara Jayasekara. This is uneven terrain, the traveling robot. You can see, although the terrain is uneven, like still the robot is able to travel through that. And so this is a carom playing robot. You can see there is a camera on top, and the camera sees the carom board, and then the robot is able to locate the disc and execute a fine shot to send the pieces to the pots. So these are beautiful projects, actually, slightly advanced projects. And then you can see our deep learning work, object detection in 3D, and then I think this is a panoptic segmentation work is also there. Then our camera design work, we design a camera from scratch and build that and put a neural network inside the camera. So this is also like 3 robots working together to build a toy building. You can see the robots, and they are also being watched by a camera. That's why we know the location of the robots. So this is a collaborative robotics project. And of course, you can see the aircrafts under Professor Rohan Munisinghe, these aircraft projects. So these are the exciting things that we do in the department. So you are most welcome to contact me and ask any question that you have. We want to distribute the knowledge that we have. This is the purpose of doing this program. So we have built a lot of knowledge, and we think that knowledge is available only to maybe 115 students every year. So that is the number of seats that we have in the department and the available space in the laboratory classes. But through programs like this, Dr. Charles kindly agreed to conduct this program for you with the support of other lecturers. We are able to make that knowledge available to you. So you can see that so many courses, maybe they are available to you. But you can see we at the department have the true practical knowledge, so which is applicable in the industry, and theoretically correct knowledge we have. So we want to distribute that knowledge with you. So that is the program. So my suggestion is faithfully participate in all the lectures. Listen to them carefully. And please engage with the lecturers. Now, this is not like watching a video. The lecturer is conducting the lecture for you right now. So it is better to ask questions and get your doubts clarified. That's why we do it live for you. Otherwise, we have the recording from the last year. We can play the recording for you. That's not the purpose. We want you to ask questions and get them clarified. I'm sure there will be many opportunities to ask questions through either chat or you by raising your hand and asking, or maybe we can make the Slido also available to anonymously ask questions. Then get the best knowledge possible. But that is not the end. So just gaining knowledge is not sufficient. You have to build a circuit by yourself. The first circuit can be simple. The second circuit can be slightly more complicated, and slowly, step by step, go forward in this. And then by the third or fourth circuit, fifth circuit, maybe then it is time for you to do it for someone else. Contact with the industry, do some little thing. Maybe you can do it for your village community or your temple. Do some embedded systems circuit, or maybe to automate your home some aspect. Then you will gain confidence. And if you are connected with us through our WhatsApp groups and emails and so on, maybe we can put you in touch with industry also, who may want to employ you or get your services. so that we can create a good embedded systems community in Sri Lanka, so that it is beneficial for the economy of our country. So the country is spending so much money on our university and our department to be able to teach you. ඔබට උගන්වන්න තමයි රටේ ජනතාව සහ රජය විශ්වවිද්‍යාල වෙනුවෙන් මුදල් වියදම් කරන්න ඔයගොල්ලෝ දන්නවා. එතකොට අපි ඒක ඔබ වෙනුවෙන් බෙදාගන්නේ දැනුම ඔබටත් යම් කිසි දැනුමක් අරගෙන යම් වැදගත් කාර්යයක් කරලා ඔබත් යම් මුදලක් උපයාගෙන රටටත් ඒක ප්‍රයෝජනයක් වෙයි කියන බලාපොරොත්තු වෙනවා. So expectation is that so the better economic benefit for our country. That's why I'm very thankful to Dr. Subodha Charles. Dr. Charles is a very busy person, but you don't see it when you see him speaking. And all the other lecturers, we are very thankful to Dr. Hasantha Malavipathirana also. And you can see that she stayed up past midnight to talk to you, and all the lecturers who are joining from different parts of the world. So thank you, Dr. Charles, for the opportunity given to be talking to these exciting enthusiastic students. I'm very happy that many students are connected. So I hope they would get the maximum benefit out of this course and obtain the certificate given by the Department of Electronic and Telecommunication Engineering. Thank you, and I wish you all the very best.
Thank you, Dr. Ranga, for those remarks. I think the participants got a very good understanding of why we are doing such courses as a department and what our capabilities are to put us in a position that makes us eligible to conduct these kind of courses. Thank you again. Right. With that, let me move on to the next session. It's now time to give an overview of what the course is going to be about, and I'll be conducting that part. As Dr. Ranga Rodrigo mentioned, today we'll be mainly telling you what we will be doing in the course and giving an overview. Starting from day 2, it will be lectures combined with hands-on sessions. So we'll be coding, we'll be developing things with you. Today might be a little bit boring because we are speaking and you are listening, but after day 2, it will not be just us speaking and you listening. You'll have to work with us. That's the whole point of doing these live lectures, so that you get stuck somewhere and then our lecturers will be there to help you. So we'll do these sessions throughout the course. We'll teach you the theory, that will be a lecture, but we'll have hands-on sessions as well, where you can engage together with us and build something together. So what you will be building, that is what I'll be touching next. So quick introduction to the course, and before that, Dr. Ranga Rodrigo gave an introduction about myself. So I graduated from the Department of Electronic and Telecom, and I got my PhD from the University of Florida. I specialized in embedded system security, and now I'm working as a senior lecturer at ENTC. And before joining ENTC, I gathered industry experience from Zone 24/7 in Sri Lanka and at Intel in the US. So throughout this talk, I'll take about 30 minutes and we'll give an overview of what the course is going to be, what we'll be teaching you in the coming 15 days. If you have any questions, I'll keep this slide on for a few seconds. You can go to slido.com, you can add the pin, or you can scan the QR code. Everybody is very familiar with QR codes these days, so I don't think it's an issue for you. Scan this, go to Slido. If you get any question while I'm speaking about the course, you can just drop that in Slido. Or else you can send the questions through Zoom, or else we actually prefer that if you unmute and speak, that will lead to a better interaction, right? So hope that gave you enough time to go to slido.com and put the pin 3188407. That's 3188407. I'll show this to you again so that you can log in, or else you can simply use the Zoom chat also. Right, so I will not spend too much time explaining what embedded systems are to you. You already got that idea when Dr. Hasantha was giving her keynote. So basic idea is that you can see embedded systems everywhere. No matter where you look, most likely you will be using one of these things, or you will be seeing one of these things, and these things being embedded systems. So it's widely regarded as the future of computing, because now we are moving away from the general purpose computing paradigm into more application specific computing platforms. So when you look at embedded systems, you can divide this huge area into 4 main categories. I'm sure you have seen an IC. So somebody has to design and develop these ICs. That is where the area of computer architecture comes into the picture. So we have a hardware aspect to this. We have sensors, we have actuators, and as I mentioned earlier, we have the ICs developed by someone. So this is the hardware domain. People work on designing these hardware components. Then we have the software side of things. When you are given the microcontroller or the microprocessor, somebody will program this. That is software. And people might develop operating systems that run on top of these microprocessors, and on top of that, you will develop other applications also. Then we have the communications aspect to this. Dr. Hasantha and both Dr. Ranga also touched upon the IoT aspect. So IoT is nothing but distributed sensors or edge devices, embedded systems communicating with each other. So for that, the communication component is crucial. People are nowadays talking about 5G, all these researchers. And the last piece of the puzzle, when you develop something, it has to look good. So then people think about how can we make a nice enclosure, right? So we will not be touching on enclosure design, of course. Throughout the course, our focus will be here. We'll be talking about the embedded hardware and the computer architecture part of things for a little. And then the main focus will be on programming, putting things together, developing the embedded systems throughout the course. So that is where our focus is. We'll not be focusing that much on communication. We'll be touching on that because we'll have an IoT component. Enclosure design, we will not be touching in this course. I'll get to that. We're actually planning for an advanced course right now that will cover all these areas. I'll get to that at the end of my presentation. If you have the skills in these areas, there are many global and Sri Lankan companies willing to get your services, willing to employ you. So that is where we want you to end up in at some point, being valuable contributors to this whole industry of electronics. So in the earlier slide, I showed you the global players, and now Dr. Hasantha in her talk also showed some of the companies that we have in Sri Lanka. This information I got from the Export Development Board website. So this is the current status of the electrical plus electronics industry. When you look at the global market, these numbers are very, very small. So we need more and more people getting into this domain, which is how we can drive this industry forward. Why this is important is when you look at Sri Lanka and the GDP, the Sri Lankan economy, you can see that most of our contributions are in the service sector. And some of our product exports, they mainly fall into like tea, rubber, and the apparel industry. Our high-tech exports, that is where electronics also come into the picture, they are very low. When you look at some of these newly industrialized countries, you can see Taiwan, China, the product-based exports compared with the service-based exports, you can see there's a huge difference. In China, it's like 10 times. In Taiwan, about 6 times. But what about Sri Lanka? The difference is quite small. So this is the product-based exports. This is the area that we are trying to develop by generating people with more skills in these areas. So this is the alignment that we are looking for with the national priorities as well. So that's a quick motivation of why we are doing such courses, in addition to what Dr. Ranga Rodrigo mentioned during his presentation. I hope that gave you an idea about our motivation behind delivering courses like this. Now let's get to what you will be covering throughout the course. Before that, let me quickly set the context about embedded system and how that is different from general purpose computing. When I say general purpose computing, some of you might be confused. Okay, what is this guy talking about? But when I show you the picture, it should be clear to you. I'm sure you're connecting to this session either through a mobile device or through your PC, your laptop or your desktop computer. So your laptop or the desktop computer can be classified as a general purpose computer, which means that you have a lot of resources. You can run many applications. You have an operating system, you install software, you download from the internet, you get a license. You can do many things with a general purpose computer. But when you compare that to an embedded system, you can see the embedded systems are typically designed for one particular application. You take a camera that is not designed to type letters. It is designed to take pictures. The software and hardware inside the camera will allow you to take pictures and not much else. You cannot write a letter. That's not possible. So they are application specific. The other example I have shown here, it's a POS machine, a point of sales machine, which accepts credit cards and can process payments. So it is designed for that purpose. So at a very high level, this is the main difference that we talk about when we compare general purpose versus embedded computing paradigms. There are some other differences as well. As you can see, I have listed them in the slide. The general purpose computers are designed to run a broad class of applications, whereas embedded run a few specialized applications. They are resource constrained embedded systems. We don't have, say, a lot of memory. We have limited computing power. So that is the domain that we are dealing with when it comes to embedded systems. When you zoom into an embedded system, you can typically see a processor, a power source, of course, and some external hardware connected to it. And you program the processor so that it will do what you want it to do. And you do the programming using a host machine, typically a desktop or a laptop. You write the code, and through a programmer, you program the processor. Typically these days, this programmer debugger, it does not come as an extra component. It is integrated on the same PCB. So if I take an example from one of the Texas Instruments development booths, you can see the processor, you can see the power system, and the onboard programmer debugger system. You connect to this through your computer, through a cable, through the USB port, for example, and then you program the system to make it do what you want it to do. So this is the typical structure that we deal with. You will see that in the course as well. Now, I told you that these processors do what we asked it to do. One option that we see as a processor is a microcontroller. There are microprocessors as well, which are more powerful, but one example for a processor is a microcontroller. When you zoom into a microcontroller, you can see many things. For example, you have the CPU that typically does the computing part. And you also have some memory that stores information. And you have a bus that transfers information. And you have the power management unit and the clock. The clock is responsible for synchronizing all these computations typically. So if you understand this high-level block diagram, and now you zoom into one of the industrial microcontrollers. So this is the microcontroller that is available in the development board that I just showed you. You can see the high-level components when you overlap with the structure of the microcontroller as well. You can see the CPU here, the processor support, the bus, some peripherals, and the memory. So these are the kind of processors that we will mainly deal with throughout the course. But when you go a step beyond, of course, the domain of embedded systems is much more complex. I just talked to you about the microcontroller, but to make an embedded system run, you need many other things. You will interface sensors with the microcontroller. You will do some processing, and then you will do some interaction with the environment. And these interactions we typically do through actuators. So if you zoom into a complex embedded system, here I'm showing like an overview of a car, you can see many embedded systems, not just one. Maybe for the climate control, you have one separate system. To detect whether your door is closed or not, whether it's closed halfway through, and now it will alert the driver, you need another system. For the heating, you need another. For your for your entertainment system, you need another. So these complex systems are a combination of multiple embedded systems, typically hundreds or even thousands in some instances. So we'll start from the microcontrollers, from the basics, and we'll tell you how to put things together so that you can develop more complex systems. to simplify this whole structure. If you look at this, you will freak out. Oh my God, there are so many things. But if you simplify things, what we are dealing with, we will be sensing the environment, and to process the sensor signals, we typically have what we call the analog to digital converter, because the sensors will give an analog output. So Dr. Hasantha in her session touched upon this. Once we convert the signals into digital, we'll be processing those through our embedded computing platforms, microcontrollers being one of those examples. And once you process, maybe we show some things. For that, we'll interface a display, or else we'll interface with actuators through a digital to analog converters, because the actuators will now be driven by an analog signal. So the signal, the digital signal that comes out of the microcontroller will have to be converted to analog so that we can interact with the environment. There are digital actuators as well in some instances. So depending on the requirement, we'll either convert or directly drive these actuators. So this is the simplified block diagram of embedded systems that we will deal with. So that's a quick overview of the domain. Now you know what you're dealing with. What are we going to teach you so that you will get the skills to go into this domain and develop something of your own? So here's the course outline. The sessions are arranged throughout 16 days. In the first slide, I've shown you day 1 through 7. And in this slide, in the second one, I've shown you day 8 through 16. Because we are starting this course end of November, we have decided to give a Christmas and a New Year break. We don't want you working when you're on vacation. So that's why we have a break in the middle. But this is the structure. Let me go into a little bit more detail about what we will cover throughout these 16 days. So we have structured this course such that from day 1 through 7, we'll be mainly touching on we'll get started by blinking an LED through a microcontroller, and then we'll develop a project with you. I'll come to that, what the project is. We'll mainly touch on the basics of microcontroller programming, PCB design, soldering, and putting things together. Then starting day 8, what we will do is we'll look at some advanced concepts. Basically, we'll be answering the question based on the knowledge that you got in the first 8 days, for 7 days, what are the other things you can do? We'll be getting yourself familiar with some professional tools as well. Then starting from day 13 onwards, on the last 4 days, we'll be combining our microcontroller knowledge with some IoT domain knowledge as well. So that is where you will communicate with the cloud, you will develop a dashboard, and you will develop a whole end-to-end system, which is what we call from sensor to cloud. From developing the sensors to cloud communication, seeing what it is, we'll be developing a user dashboard as well. So that's a quick summary of what the course is going to be about. Let me now touch upon the details of what we will cover from day 1 through day 16. So the content that we will cover throughout the 16 days will be centered around this one project. That is the project that I'm showing you in the slide right now. We call it the Medibox. Last year we had the same course, but now for this year we have refined the course. Last year we had a Medibox, and now this year we have a smart Medibox. So you can see we have upgraded ourselves to give you more capabilities. I'll tell you the motivation behind that as well at the end of the presentation. So this is I think at what point did you lose me?
So you were
I
talking
think yeah, very like around 5 seconds. You are on the same slide here.
Okay,
Sorry.
so I didn't lose much. Okay, my infrastructure is giving me a lot of trouble these days. Let me quickly check if I'm still recording, just to make sure. Okay, looks like we are. Right. Okay, I'll start this slide again. The content that we will cover throughout the course will be centered around this smart Medibox project. Last year we did a Medibox. This year we are upgrading ourselves to do a smart Medibox. So it is capable of reminding you to take your medicine on time. That is the purpose. For that, we'll be giving you some capabilities to configure an alarm. The configuration will happen through push buttons. The Medibox will also have a temperature and humidity sensor to make sure that the medicines are kept at the proper temperature and humidity. You can check these values of the sensors through a dashboard. That is where the cloud connectivity comes into the picture. We'll be developing an online dashboard, so you don't have to be close to the Medibox. You can be somewhere else, and the data will be given to you. So once you set the alarm, after the alarm time comes, you will hear the sound of a buzzer, and you will also see some LED bulbs, LED lights blinking to say that, okay, now it is time to take your medicine. So that is a very brief overview of the use cases. We'll be communicating with the cloud through the ESP32 chip that we have on board in the development board. And then we'll be sending data from the sensors to the cloud. We'll do some processing. We'll be sending some commands from the cloud to the device as well. So it'll be a two-way communication. And through those features, we'll be reminding you to take your medicine on time. So this is the project. We'll be centered around this project. We'll be teaching you the content that is required for you to develop such a system from scratch. That is our purpose. So that we will start from day 2 onwards. Here is a schematic and a PCB design of the Medibox that we'll be developing with you. Once we manufacture the PCB and then we populate the components, this is what it will look like. The 3D model of what the smart Medibox will look like. So that is what you will achieve as the project throughout the course. So to give you the capabilities required to achieve this, we have structured the curriculum from day 2 until day 16. So on the very first day, so today is the very first day, on the very first day of your learning curve on developing the Medibox, we'll be teaching you how to program a microcontroller. And then we'll simulate the functional components of a microcontroller using an online simulator called WalkMe. And then we'll take you from the breadboard to the schematics with a tool called Fritzing. We will continue this learning curve on day 3 also. We'll start developing now with the basic understanding you got at day 2. We'll start developing the smart Medibox in day 3. So some of the components you will learn in day 2 also, but we'll continue that learning curve into day 3. So now you can see we have connected our computing device, we have connected our display, we have connected our input, the push buttons, the LED lights, and the buzzer. So at the end of day 3, you will know how to put these things together and how to program them. All of these things we will do using the online tools where we get the components together. You can see the breadboard kind of structure here. We'll be developing based on that. Okay, so now at the end of day 3, you know how to put things together, how to program, and how to get things done. But if you are to manufacture, if you are to actually develop this and hold the Medibox in your hand, you have to take this from the simulations and the online environment to the actual hardware domain where you can manufacture the whole thing. For that, we will start by designing the schematic of the smart Medibox from day 4 onwards. In day 5, we'll be designing the PCB. So now you draw the schematic, and now you start designing the printed circuit board. And once you print the PCB, you will be able to solder, populate the electronic components, and finalize the whole thing. So in day 5 and day 6, what we will do is we will design the PCB of the smart Medibox together with you. So all these sessions, the programming, the schematic design, the PCB design, These things will be hands-on sessions, where you can work together with the lecturers and develop it together with us. So if you get stuck somewhere, we'll be there to help. Day 6, we'll look at some best practices in PCB design, what you should do and what you should not do, so that you'll not be stopping when you develop the Medibox. That's the whole idea. You develop one, you learn through the course, and you will be developing things on your own after that. So for that, we'll teach you what the best practices are. In day 7, now that you have developed the PCB, you have manufactured it, in day 7, we will teach you how to populate the PCB with components, the soldering techniques and all that, right? So that is from day 1 through 7, I told you that we'll be developing the project while learning the basic concepts. From day 8 onwards, we will look at some advanced concepts. So we'll be touching on some in-depth microcontroller concepts. We'll teach you how to program in embedded development boards. We'll be especially talking about STM32, which is a widely known, a very popular family of microcontrollers. Day 9, we will continue our discussion about advanced concepts. And in day 9, we'll be giving you a case study. So we, of course, in day 9, within one day, we'll not be able to develop another whole embedded system. We did that for Medibox throughout 7 days. In day 9, what we will do is we will take a case study and teach you how you can put together a smart plug. So it will be more of a product design thing. And another reason why we put this together is because you have the basic understanding from Medibox. Then you can know how to develop something more advanced. And we also have a plan of developing another course of similarly with the length of about 16 days, where we teach you how to develop a product, a more advanced product from the scratch. For that, we have the plan of developing the smart plug together with you. So that will come after this course. But in day 9, we will give you an overview of how you can approach that problem, what are the ingredients, and how you can put together. Of course, within 3 to 4 hours, we cannot develop the whole thing. So as I mentioned earlier, it will be an overview. And based on that, after that, you can, if you're interested, you can join the product design course as well, so that you can develop the smart plug together with us. So that's a quick overview of what day 9 holds for you. Here you can see the end-to-end pipeline of the smart plug. This is the case study that we will be covering in day 6. Right, coming to day 10. So if you can remember when I was telling you that we'll be designing the PCB through PCB for the Medibox, we use an online tool called ECEDA. But in day 10, we will teach you how to design these advanced PCBs through some professional EDA tools. So for that, we'll be using Altium Circuit Maker. That we wanted to give you a background of professional EDA tools also, rather than stopping at ECEDA. So that is the purpose of day 10. Day 11, we'll be giving you an overview of some of the more powerful microprocessors, the single board computers. And then we'll also touch on some embedded machine learning also, what you can do with these development platforms. How can you train a model, how you can deploy, what are the capabilities, how will you optimize. So we'll touch on that in day 11. Another reason for having this content in day 11 is because I'm not sure whether you are aware, but just last week, we concluded a course, a separate course on embedded machine learning. So just like the product design course, we have a separate course for embedded machine learning where we go into a lot of detail about embedded machine learning. So if you're interested, you can take the overview of embedded machine learning in day 11 and join the embedded machine learning course to enhance your knowledge as well. So this is a series of courses that we have planned. This is the first one. The microcontroller-based embedded system design one is the first course of a series of courses, as you can see. We'll be giving an introduction in day 11 to one of those future courses, that is embedded machine learning. Day 12. In day 12, we'll be looking at some best practices in C++ programming. So when you develop your Medibox, you'll be mainly dealing with an Arduino-based the IDE and that environment. You'll be using C and C++ to program that. But in day 12, we will tell you some advanced concepts. What else you can do with the language C++, how powerful it is, we'll be touching on in day 12. Day 13, right. So when I was summarizing everything, I told you 1 through 7, we'll develop Medibox. 8 through 12, we look at some advanced concepts. 13 through 16, we will look into cloud connectivity and the IoT component. So with that, in day 13, we'll get started with our communication side of things. We'll show you how we can deploy an IoT system based on the Medibox that you have developed so far. So I hope you understood that in the first 7 days, we'll be doing things without any connectivity with the internet. We'll put things together, do the PCB, we'll solder the components, and we'll have a functional Medibox. Starting from day 13, we will connect that to the cloud. And once you connect it to the cloud, the sensor information you can monitor through a dashboard. You can see when the next alarm is going to go off. You can set the alarm through the cloud. Rather than having the device with you physically, you can do the configuration from the cloud as well. So that is the journey we will start from day 13 onwards. On the first day, we'll give you an introduction. Day 14, sorry, not on the first day. Day 13, we'll give you an introduction. Day 14, we will introduce you to this platform called Node-RED. That is an online tool that you can use to develop a dashboard rather than you having to develop a software from scratch. So even if you have no knowledge of these, web development technologies, you'll be able to develop a dashboard through tools like Node-RED. So we'll give you an introduction, what that is, and we will develop a dashboard together with you. That exercise we will continue into day 15 as well, where we use Node-RED and we complete the end-to-end pipeline from the sensor, how to configure that to access internet, send data, and see the data coming through the Node-RED platform. That is the focus of day 15. And finally, we will put things together, we will conclude, and we will give you some insights about the future steps as well, what you can learn based on what you have covered throughout these 16 days. So that's it, folks. That's what we will cover from day 1, that is today, until the end of the course. So throughout this journey of learning things, you will be familiar with many tools that is used in embedded systems development. The online simulators, the EDA tools. Let me show you some pictures of what the simulators and the tools look like. This is the first platform that you will be familiar with. Then we will do the use FreeSync to draw the circuit diagrams. We'll have the ECEDA tool to draw the PCBs and the schematics. Then we'll go into the more professional tools, the Altium Circuit Maker. Of course, the Arduino IDE you will use to program. The Microchip Studio, this is where we will do some of our programming stuff. Then we have the STM32 platform. When we specifically talk about some of the advanced microcontroller concepts, we'll be touching upon this. And the Node-RED dashboard. So you can see it looks very nice. Without a lot of knowledge about web development technologies, you can be familiar with these tools that kind of abstracts the whole web development process, gives you the tools where you can easily put something together rather than developing something from scratch. So that's the purpose of Node-RED. And we'll also touch on VS Code, a very common tool used among developers. So those are the tools that you will be familiar with when you go through the course. Right, so again, a quick reminder, if you have any questions about the course content, please drop them in the chat. We'll be happy to clarify. Kitmin has sent the link to Slido on the chat also, so you can simply click on that, ask any questions. I'll open Slido once we are done with the introduction. All right, so now you know the content that we'll be covering and the tools that you will be familiar with. Now you might be thinking, okay, this is a embedded systems code, embedded systems course. Do we need hardware? Right, might be coming to your mind. Well, let me answer that. For the successful completion of this course, you don't need access to the hardware. What that means is you can complete the assignments, you can earn the certificate based on software tools. But we want to give you the skills of dealing with hardware as well. So for that, you have two options. The first option is you can acquire the hardware, or else we will arrange some lab sessions at ENTC where you can come to the university. We'll make the hardware available to you. You can, put things together and see for yourself. So those are the two options. The approximate cost, if you choose the option of purchasing hardware yourself and developing this during the lecture days, you can take that option. And one of the non-academic staff members at ENTC the person has agreed to purchase the hardware in bulk, and he will be sending them to you. If you are interested, that we will give that as an option. So directly interacting with our technical officer, he'll be sourcing the hardware, and he also agreed if somebody would like to get the PCB manufactured, he will be providing those facilities as well, right? So the approximate cost for getting the components to develop the Medibox, for the PCB manufacturing, soldering, and also to package them and to send it to you wherever you are within Sri Lanka, the approximate cost is about 7,000 rupees. So you have multiple options here. For example, you can choose to purchase the components without getting them soldered, and you can solder yourself. Maybe you can manufacture the PCB yourself as well. We will teach you how to do that. That is an option. Or else you can send us the design and we will send you the manufactured PCB. That is also an option. Once you manufacture the PCB, you can solder the components yourself, or you can tell the technical officer to solder them and send it to you, right? So depending on the level of details that you would like to go into, the level of experience you would like to gather, all these options are available to you. And if you decide not to purchase through the technical officer, it's totally fine. We will send you the bill of materials and we will tell you the places to buy also. You can buy the components yourself and develop the project together with us. I hope the options available to you are clear. If you decide not to purchase the hardware, we will be purchasing some hardware as a part of the course. We'll be making them available through the university labs. You cannot take them home, of course. You can come to the university. We'll arrange those laboratory sessions, and you can play around with the hardware. You can put things together, and you can see how things work by yourself. So that's about the hardware requirement. I hope that's clear. Please send questions in Slido if you're not clear. I think you are aware that we'll be giving away a certificate for those who complete this course successfully. So what does it mean to complete the course? Well, we'll be evaluating you based on 4 assignments. And if you pass these 4 assignments, you will be eligible for the course completion certificate. We will not be taking attendance because you might have other plans on some given days. I know that we are taking 8 consecutive weekends. There's a break in the middle, but every other day you will have to join. But for some reason you are unable to come, then we will make the recordings available through Moodle. I'll come to that. We will not be taking live attendance. That is not our purpose. You can watch the lectures at your leisure, but we highly recommend you come in person to the lectures. Sorry, not in person. You join virtually to the lectures in real time, simply because then you can take part in the hands-on sessions. You can develop the systems together with our lecturers. So we highly recommend, but for whatever reason you cannot come, we will make the recordings available through our learning management system, that is Moodle. So either way, no attendance taken. You have to complete the assignments to be eligible for the course completion certificate. That will be our evaluation criteria. The first assignment will be drawing a wire diagram with fritzing. The second one will be simulating the functional components. So you have to turn it in, what you have done. Third one, the PCB design. And finally, the dashboard that you will develop with Node-RED. So you can see, we will teach you how to do these things. We will work with you. We just expect you to complete them yourself and submit the assignments. So it is not completely different. This is what you will be developing through the course. You can develop it with us and submit the assignments. So I believe it will not be very hard for you. hopefully all of you who are starting the course will be able to complete, and we'll be as flexible as possible. We want to make sure that you get the knowledge and also the certificate, so that you can, you have a proof that you got this knowledge. So it'll be flexible and try to accommodate everyone as much as possible so that you can complete the assignments. Hope you're clear about the evaluation criteria also. That's it for the course overview. All of these things will be facilitated through these the panel of lecturers that we have put together. Several people are right now outside of Sri Lanka, so they'll be joining from different places, and they have generously agreed to conduct the courses at a time that is convenient for you. For example, Kitmin and Abarajithan, they are both in Pacific time, so that will be middle of the night for them, based out of Canada and San Diego, respectively, British Columbia and San Diego. So that is what you can expect. Right, so we have structured the entire course to be outcome oriented. What that means is we give you hands-on experience and the fundamentals. We combine the fundamentals with real-world applications. The panel of lecturers have spent a lot of time designing the course. We have custom made the curriculum so that you can design the smart Medibox and learn the fundamentals around developing the smart Medibox. So that is the whole idea. You can see that we have inverted the traditional teaching method where we tell you the theory and we allow you to explore the applications. That is the traditional method. But here what we are doing is we are fixing an application, that is the smart Medibox, and we are giving you the ingredients that will make you capable of developing the smart Medibox. So we are taking like an inverted approach where it's an outcome oriented approach rather than being process oriented. So a few quick remarks before I conclude. We did the course last year in 2021, and we got some good feedback and we got some points for improvement as well. So with that, last year we did 2 projects. One was the Medibox and the other one was the smart plug. This year we decided to make the smart plug a case study and develop the smart Medibox with the IoT capabilities inside the Medibox as well. The reason for doing that is through the feedback that we got from the students. Some students said that the last few weeks, we covered a lot of content within a short amount of time. So it was not easy for them to understand. So we took that feedback into account. And as you can see, what we have done is rather than developing 2 projects, we'll be developing 1 project, but we will still cover the same theoretical concepts, taking more time. So allowing you more time to understand these concepts and get up to speed. So even in this course, we'll be asking for feedback from you. So please let us know what you think. If we have to improve, even in the middle of the course, we are willing to do that. The course will be taught in English. If somebody is having any language difficulties, we'll be happy to give Sinhala and Tamil explanations as well, if you request. And on each day, we'll be allocating some time for questions and answers. You can clarify any questions that you have throughout the process. If you complete the course successfully, this is the certificate that you will be getting. This is the front view of the certificate, and this is the back view on the same page, 2 sides. We'll be giving you a small transcript outlining what you have covered and the qualification also. So hopefully you'll be completing the course, and once you gather the knowledge, you can do many things with the knowledge. Maybe you will be contributing at your current workplace with the knowledge. Maybe you will get promoted because you have more skills. Maybe you have a problem that you want to address. For that, you will develop a product. You never know. And you might even go into teaching, distributing the knowledge that you gathered to other people. So all these things that you can do in the future, it requires you to understand the fundamentals, learn with us, and explore on your own. We cannot cover the entire embedded system domain through 16 days. We'll teach you the core ingredients, and then we'll give you some materials that you can refer to in the future also. And with that, we expect you to explore on your own, learn on your own. And if you decide, you can join our future courses as well to gather more information. Couple of quick reminders. From day 2 onwards, we'll be allowing access to the course only to those who pay the course fee. Let me quickly go to Moodle and show you what those terms and conditions are. Please give me 1 second. Just got a notification saying my laptop battery is about to die. I don't want that to happen. So let me quickly plug this thing in. Right? Can someone confirm whether you can still hear me?
Yes.
Perfect. I will go to our course web page and show you the instructions that we have set for you. Hope you can now see the browser instead of the slides. So yeah, if you go to this, we will send you the bit link on the chat also. I'm sure you are aware of it. We sent you text messages and emails also with the link to the website. This is where you have to go to the microcontroller-based embedded system design page of the NTC website. You can see the instructions over here. We have sent the same instructions to you as an email, but we have added that as a PDF over here. So the payment deadline will be on the 30th of November. That is next Wednesday. So you have time to decide whether or not you would like to take the course, continue after day 2 onwards. If you decide to do that, we have given you payment instructions. Once you do the payment, please fill this Google form and submit your information together with the payment receipt. About the course fee, typically the course fee is 20,000 rupees for 16 days. But for undergraduate students and pre-university, so pre-university, what we mean by that is students who have finished their A-levels and waiting to go to university, there's an intermediate period. So for current undergrads and pre-university students, there'll be a discounted rate of 16,000 rupees. And for school students, there can be school students joining because this is a beginner's level course. If you're willing to put in the effort, even a school student can complete this. The fee will be 12,000 rupees.
Dr. Charles, there was a question directly asked from me for NDT diploma course students, whether there will be a reduction.
Yes, then we'll be considering them in the category of current undergraduates and pre-university students. Yes.
Thank you, Dr. Charles.
Yes. Anybody taking tertiary education, that is education after your school, will fall into this current undergraduates and pre-university students category. Right. So that's the quick overview of the course fees. And if you are interested in getting the hardware, please complete the Google form and let us know that you would like to get it. It will help us get a head count about number of people who would like to purchase the hardware, and we can facilitate that. You know, it's a little bit tough these days to acquire electronic components. There's a global shortage. That is why we are getting this expression of interest in the beginning. So we know how many people are willing to purchase, and we can place a bulk order and get everything at the same time. Right, so that's a quick summary of what you have to do if you would like to continue in the course. Let me go back to the slides. Hope that is clear. The hardware I already touched upon. So this is the link to the website, the bit link, ENTC-microcontroller. Please go there, and you can see the screen that the web page that I was just sharing. You can get more information through that. So you know the evaluation criteria. You must complete that to obtain the certificate. As I mentioned earlier, attendance will not be taken. For everyone who register, who pay and register, will be enrolling you into the learning management system, that is Moodle. You can expect to get credentials to that. Then all the recorded lectures, the assignments, the slides, we will make them available through Moodle. We'll be creating a WhatsApp group based on everyone who pay and register for the course. We'll be creating the group, and all the announcements will be sent there. So when you enroll, we'll be asking you for your WhatsApp number also. Please provide us with that. If at some point you realize that you are not in the group, please let us know. We will quickly add you to the group. Keep the website bookmarked. We'll be adding all the details, even the recorded lecture from today's session, we will upload in the website. Hopefully by before the end of today, we'll set it up, and we'll also notify you through a text message and through an email. That's a quick overview. I think I took a bit more than 30 minutes. Sorry about that. Hope you can do some jumping jacks if you're bored and feeling sleepy. And in the meantime, if you have any questions, this is the Slido link that I showed you earlier. Go to Slido, add your question. We'll be answering some questions that you have right now. Let's see. Yeah, there's a question in Zoom chat. Can we have the component list that we need to purchase? Yes, we'll be sending that in day 2 or 3. For those who continue with the course, we'll be sending that information. Okay, let's go to Slido and see whether we have any questions. If any of our lecturers, instructors, if you got any questions as direct messages, please let me know. While we wait, I'll go to Slido. Oh, we have several questions. Let's try to answer them. Right. Okay, where do we start? Right. Okay, we'll start from the bottom. Is there a discount for postgraduate students? Well, unfortunately, we consider postgraduate students in the same category as industry because you have obtained your first degree. So then in that case, there will not be a discount. It will only be available for undergrads and school students. Hope that's clear. If you have any special requests that justifies this, that's the general policy that I told you about postgraduate students. If you have special circumstances, please send an email to the given email address. You can see the email as a comment here. Then we will evaluate that request on a case-by-case basis. Next question: are PIC microcontrollers included in this course? No, we are not dealing with PIC in this particular course, mainly because PICs are outdated. Do we get to use STM32 related projects and programming in this course? Yes, you will not be using an STM32 microcontroller. It'll be done through the online tools, but you will get the background. Yes, how to deal with STM microcontrollers. We'll have one day that is dedicated to that. Another question about installments. We actually don't. Again, we cannot encourage this widely simply because of the way that finances function in the university. It'll be very hard to keep track of things. That is why we do not give this option. I think this is the same person. So please send an email. We'll evaluate that again, as I mentioned earlier, on a case-by-case basis. We'll try to accommodate, because we would very much like to give the knowledge to people. We at any point, our intention is not to block you. So we'll be as flexible as possible. But of course, as you can understand, as an institute, we have some limitations. So we'll have to adhere to those. We'll try to push those as much as possible. Okay. What is the microcontroller we are using for this course? I think the answer is already here. The Arduino Uno board, and we'll use, yes, some ESP32. Sorry, Kitwin, you were saying something.
Oh, no, I was saying the ESP32 is the main one. The reply
Yes.
below that mentioned it.
Yeah.
There's one more.
Yeah. Oh, okay. Yeah. Okay. Do we have any physical labs? We are planning to have, yes, because we would like to see you in person also and allow you to interact with these components. So yes, the exact date, because we have to get permission from the university to allow outside students to come into the university. So it includes a bit of processors. So we'll keep you informed about what the dates are and how we will move forward. That will happen in the middle of the course. We'll let you know. Can someone who couldn't register earlier can pay the course fee and register now? I think you are referring to those who could not submit the initial Google form. Yes, that is possible. If you go to the website, follow the instructions, complete the payment and register, we will still count you in. But please make sure you do that before the payment deadline. That is before the, I think 30th Wednesday is the deadline. So make sure you do that. Then we will consider you in the course. Right. There's a technical question, not directly related to the logistics of the course, the difference between a programmer and a debugger. Well, programmer is basically you're programming the microcontroller, but through the debugger, you can do more things. Like the whole idea of a debugger, if something goes wrong, you should be able to see where it went wrong. So it includes some added capabilities. Right. Is this course free for ENTC students? Well, we will allow the ENTC students to audit the course, but only those who pay the course fee will be eligible to get the course completion certificate. Because we are doing this through the department of ENTC, we'll allow you to audit the course, meaning you can attend the lectures, but only if you pay the course fee, you will be able to get the course completion certificate and get access to the Moodle platform. So live lectures, ENTC students will be able to come, but you will not be able to access Moodle. You will not be able to get the course completion certificate. Right. I think we covered everything, all the questions that came in. Dr. Ranga has forwarded a direct message that came in. I think I have answered that now. That's about the students at ENTC and how we are handling that. Hope the process is clear. Did we get any other questions? Anyone else?
There are some additional questions below. If you go below, five questions.
Okay. Just came in. Okay. Right. Can you let me know what would be the next advanced course after completing this? Okay. Can I enroll for the other advanced course parallel to this course? Well, we have not started enrolling students to the other advanced course yet. It will happen in middle of 2023. The exact dates we will let you know. Yes, what the course will be about. In the course introduction, I told you that in one of the, I think it was day 9, if I'm not mistaken. On that day, we'll give you the case study of the smart plug. We'll be expanding that and developing the smart plug with added features. For example, the smart plug that we had in the introductory level course, it only monitored DC power. But in the advanced course, we'll be able to plug that into AC power. We'll look at power management, isolations and all that, and advanced PCB design, all those things, starting from the microcontroller programming, the advanced PCB, putting things together. And we also have a few sessions on designing enclosures, mainly using SolidWorks. That will be the focus of the advanced course. The enrollment for that, we will start middle of 2023. So please stay tuned with social media and the department website. We'll be announcing, similar to the last time, we'll be giving you like a month. We'll run promotions for about a month and a half. During that time, we expect that you will see those promotions. And if you're interested, you will enroll in the course. Hope that's clear. You cannot enroll in parallel because we are doing the advanced course after this one. Question, another one. Yeah. I mentioned about a series of courses. Can you give some info on next courses and the timelines? Well, the exact starting dates we are yet to finalize, but another course that we have planned right now, it is something slightly different from the embedded systems track. We are also planning to develop a track called computer architecture, where you will learn how to develop a processor. So we'll use System Verilog mainly for that. We are planning to release that course in February of next year. And after that course, we'll be taking the Advanced Embedded Systems course. So the February course on computer architecture is again a beginner's level course. Those who have no information, no background of hardware descriptive languages will be able to take that. And from the scratch, you will be able to learn how to develop components of a processor. So in this course, what you are learning is when you are given a microcontroller or a microprocessor, how to program that, right? And put other hardware components together and develop an embedded system. In the computer architecture, the other course that I told you about starting in February, we will teach you how to design such a microcontroller. Okay, that's a starting point. Of course, in the course, we'll not be able to go up to the level of a microcontroller, but some of the key components, mainly the processors part of things, the components we'll be designing using System Verilog. Like an ALU, for example, we'll tell you how to put that together, write the code on System Verilog, simulate, verify the functionality, a matrix multiplier, for example. So we have identified a few components that we can cover within 16 days. We'll teach you how to do that. And the plan is to have another advanced course where you put things together and develop an entire processor. So we have actually planned a series of courses where within 16 days, we can give you like a tangible outcome. And through the beginners and the intermediate level courses, if you follow them, you will be able to get a lot of good knowledge about embedded systems, computer architecture, and so on. Right. So that's the plan for 2023. This is the first course of a series of courses. Right. I hope that clarified. I'm unable to give you exact times for the other courses. The February one I told you about, we'll start advertising for that somewhere in December, so that you can know the exact start dates and the schedule for the beginners level computer architecture course. Is there a deadline for the assignments? Yes. When we release the assignments, we will be setting deadlines, and those deadlines will be reasonable. So you'll have more than enough time to complete them. We will keep you informed about those. There are discounts for undergraduates. I hope that's clear. Yes. If you're doing your first degree, whether it's full-time, part-time, there'll be discounts for undergrads. Another question, can we know what are the courses available? I think I answered that in the previous answer. Another question, can we mention the lecture times? Yes, as the moderator has given the answer, if you can go to the website, we have given you the schedule. So let me go there quickly. We have given you the schedule. So we just concluded the embedded machine learning course. We will have another iteration of that embedded machine learning course towards the end of 2023, hopefully. In that course, we were able to stick to the schedule. We did not reschedule any lectures. So we plan to follow the same practice. So if you have any plans, you can arrange around this lecture schedule. This is the break in the middle. And until 18 December, we will have back-to-back lectures on every weekend. And after 1st of January, we follow the same structure until the end of the month. On 29th, we'll be concluding everything. For the embedded ML course, on the last day, we had a closing session in person. You might have seen the pictures circulating around on social media. So we plan to do something similar for this course as well. Right. Let's go back to the questions. So I've spoken non-stop for 1 hour. Okay. Do the certification combine with some NVQ levels? No, it does not. We have not gone through the Sri Lanka quality assurance framework. So you will not be able to combine. You will only be able to get a skill and the certificate. So of course the ENTC certificates has some level of validity. We cannot compare that with NVQ level exactly where that is, because this is only one course. NVQ levels are typically for longer duration courses and diplomas and degrees. So we are not in that position yet. Hopefully, maybe in the future, we can align with that hierarchy as well. Last question, assuming that I did not miss any questions, is this useful for CS students? The moderator has also given an answer. Yeah, we think so, because when you think about it, the boundary between electronics and computer science and even other domains, they are very thin. There is no huge boundary between these domains. So if you are a CS student, getting a background of electronics embedded systems can definitely be helpful. And there's a significant programming component to this. So it'll be easy for you to get up to speed as well. So I hope I answered you. Okay, I checked the Zoom chat. No more questions coming in. I hope we covered everything on Slido also. If any of the other lecturers would like
Dr.
to
Charles, there's
add
a
anything.
question asked from me.
Yes,
Is
sir.
the certificate online?
No, it will be delivered to you as a mail, not email, as a post. You will get the hard copy in your hand.
The certificate will contain the signatures of Dr. Charles and me.
Yes. So once you complete the requirements for the course, those who complete the course successfully after completing the assignments, we'll be sending you the certificate. Of course, we can. There'll be a QR code also in the certificate, and if you show the certificate to someone, the person receiving the certificate will be able to validate your credentials. So you scan the QR, it'll take you to the ENTC website where we say that this certificate is valid. So there's that validation process as well. So you can think of it as both as a hard copy and a soft copy. Any of the other lecturers, if you would like to add anything on top of the answers I gave, please feel free.
I think everything is covered sufficiently. Thank you.
All right. Thank you, Gitmin. I'll give you a couple of more minutes. We'll take a short break anyway, because we've been doing this for about 2 hours now. And we'll have another session that will take about 30 minutes. That's the very first, a bit more technical session with a brief history of microcontrollers and what the industry looks like today. So that will be delivered by Mr. Abarajithan. I think he's already in the call waiting to get started. Yes, he's there. I got another question just now on the Zoom chat. Okay, it's more of a comment rather than a question. So the person would very much like to meet everyone in person, come to the labs and develop the projects together with the team. So we will see how we can facilitate that. We will at least get everyone together at least for one day. If you would like to come, again, that is optional. Even if you cannot come, you can still complete the course. It's not mandatory. But for those who would like to come, get the hands-on experience, we'll be making those options available throughout the course. Any other questions? Right. Abba, I know it's the middle of the night for you. Let's allow people to take a quick break. Can we start in 7 minutes? That's Sri Lanka time, 3:25 p.m. Will you be okay with that?
Yes, sir, that's fine. In how many minutes?
7. Let's just a quick break and we'll come back at 3:25.
Okay, sure. Yes, sir.
Okay. Right, guys. In the meantime, if you have any questions, please keep them coming. We'll take a quick break. We'll gather at 3:25. Please stretch yourself. Sitting in one place for 2 hours is not easy. Maybe you are not sitting. Maybe you are attending to some other stuff as well. But anyway, we'll take a quick break of 7 minutes. We'll come at 3:25 Sri Lankan time and we'll get started with our next session. Let me quickly. Well, you know what? The showing part, we'll leave it to later. So we'll come back at 3:24. Hope to see most of you here for that session conducted by Abarajithan. Okay, I hope we can get started again. It's 3:25. Without delaying any further, let's get going. Right, so the next session, as I mentioned earlier, will be delivered by Abarajithan. He's also a graduate from ENTC, and currently he's working as he's studying as a PhD student and also working at the same time at the University of California in San Diego. Before moving to San Diego, he was a lecturer and also a consultant at ENTC. He also worked at Lemurian Labs, a Canadian-based company, as an RTL design engineer. During his internship, he worked in CCRO in Australia. So as you can see, he has a wealth of experience. He'll take the next 30 to 45 minutes to tell you a brief introduction about microcontrollers, what the industry looks like, what the history looked like, and where we are right now, and where we can go from here onwards. So hope that will inspire you to learn more about this domain, with the very exciting domain of microcontrollers. And after that, from day 2 onwards, you'll deal with those microcontrollers yourself, and you'll develop something tangible, which is the smart Medibox. So to begin all that discussion, I'll hand it over to Abba to conduct the session.
Sure. Thank you so much, sir. So, yes, let me share my screen.
I think Abba is having some connectivity issues, right?
Yes, I'm sorry, I think I have some issue with my screen share. Let me try again.
Yeah, it says started screen sharing, but we cannot see it for some reason.
Hi, Abba. Can you hear me? Hi, Abba. Can you hear me?
We can hear you, Kidmin. Abba doesn't seem to hear you.
Okay. Abba, can you send the link to the slides?
Hold on,
Oh,
okay.
now you can see it.
Yeah, we can see it now.
Can you see now?
Yes.
Yeah.
Yeah, so sorry about that. Yes. So
But if you're
think-
saying something, we can't hear you.
No, I think Abba is getting disconnected when he tries to share the slides.
Right. Yeah, he just dropped a text saying Zoom keeps crashing. The same thing happened to me. I've done many online lectures, but it never happened. But today it happened. Not sure why.
Shall we share the screens and then Abba can just narrate the slides?
Yeah, let's try to do that. Did you get the slides from him?
Oh no, I need the link.
Yeah, that's
I'll ask him.
sorry for the technical difficulties, folks. Please bear with us.
Can you see now clearly?
Yes, we see the PowerPoint window, not the slideshow, but that is okay. Okay, now we can see the slideshow.
Okay, great. Yeah, sorry, I think it's a resolution issue. Okay. So let's start. So this session is about to give an introduction to microcontrollers and product development, to give an overall idea of like what we are going to do and like how it connects with the rest of the industry as well as the history of like electronics. So Dr. Subodha, he gave me like a good introduction about me. So I'm mainly working on designing chips. So it's like VLSI design, so designing microprocessors and stuff for energy efficient ML implementation for neural networks, right? So that's what I have been working on. And yeah, so this session is going to be like kind of an overview of the entire electronics as well as product development. So I'll be saying some interesting stories behind electronics and how things have changed over time, as well as what are the things that you will be focused on when you go for like the industry and so. Okay, so let's go back a bit in time. So the story of electronics is basically begins with, you can say it begins with the telecommunications, right? So we have the first commercial telephone in 1877. So it was like a very simple device. So you have like on one side you speak in a mic, and on the other side like the signals are directly transmitted to the other side, you have a speaker, right? So it was the very simple, very basic first telephone device. Okay. So but the issue was like there was no amplification. So then like you could not hear the sound clearly on the other side. Okay, why? Because the mic, when you speak into a mic, like just like I'm speaking into a mic right now, it produces a very small voltage difference, right? Which is not enough to drive a speaker. So there's no amplification. So like people have to like get into like these telephone boxes and like scream on top of their lungs to get it working. And it was like one-to-one connection, like from house to the shop or something like that. Something less than 3 miles. Why? Because the signal will, when you go further and further, several miles, your signal will go down. Signal strength will go down, and there's no way to amplify it. So this was the very basic, very simple device in the very beginning. And then with time, so yeah, so over time, like this was improved. Okay, so this was improved, and then you have like stuff like vacuum tubes, right? So vacuum tubes were invented as amplifiers. So that is the main reason for this, and it was the communication industry, the telephone industry that pushed most of the development in electronics, right? So the biggest problem they had was this: like, you can only talk for like 3 miles. Okay, and that also like it was very difficult. So you need some way to make this small signal, which is generated from speaking. You need to make it bigger, enough to drive a speaker, right? So for that, you need actual amplifiers, analog amplifiers. So then they did a lot of research, and then there was not a lot of physics behind it. So they tried all sort of things like force hairs and like different metals, or randomly like anything they could try, and finally came up with like a certain design of stuff like the vacuum tubes. And they like the materials were chosen kind of randomly, right? And so that was like a big break. So like in the industry. So for the first time, they like laid a telephone line from one end of America to the other end of America. So it was the Bell Labs, like the Bell company. So they did that, and then like they made the first long distance phone call using vacuum tubes. And then like so that became so popular in 1930s. You even have like radios. So like people were carrying around radios like at homes and everything of vacuum tubes. Okay, so the way it works is just like the today's radio. You have like a very simple, like very small, what the antennas, they get the electromagnetic waves, and they produce a very small signal. Okay, and you need to amplify that signal to like hundreds of times, so thousands of times, to hear something, to into a voltage that can drive the speakers, right? So again, for that, they like the vacuum tubes were the actual amplifiers. Okay, so here you can see like an older radio. So this radio was like it was bigger than a microwave oven, right? So people, the rich people, they used to have it at homes, their homes and everything. It was very difficult to maintain. It's not very clear, and these tubes, they blow up often. Okay, so they heat and they blow up often, and they take a lot of power. They produce a lot of heat as well. So this was like not very kind of like there was still room for improvement, and they still use these vacuum tubes to do like long distance phone calls, as well as like switching, like to what connect between multiple systems. You had like switchboards, okay, and the switchboards were like manually done by people, right? And so you had that sort of like a mixed situation in 1930s. And then in 1945, there was like the most important invention of the last century. So that was a transistor. Okay, so transistor is like a solid state device. So which means like it's a piece of silicon which you get from sand, right? A small piece of silicon, which can actually do the same job as a vacuum tube, but much better. Okay, so it was revolutionary. And then that became like super famous, and like all the companies started using it, and they started improving the designs. Within like 10-20 years, everywhere, like around the world, people were having transistor radios. Okay, so these were like handheld radios. So now you have like a lot of transistors, like one made into like circuit boards into handheld radios. So the same thing that like an oven-sized device that could do, you can do it in a handheld device. Okay, so this made like everything small as well as low power and cheap. Okay, so this was in 1960s, and then yeah. So this is the story of like Allen Electronics. We will take like a small detour on the story of computing, because we are talking about microcontrollers, right? So the computers are not something new. Okay, so they have been, so this is a device that is 2,200 years old. Okay, so that is as old as the civilization in Sri Lanka. So like it's called anti-capital mechanism. It was used by Greeks like in the 7th century BC, and it was found on a shipwreck. Okay, so it is a mechanical computer. So you have all these like cogwheels, like pretty very precise cogwheels, which simulate the movement of sun, moon, and the 5 planets. Okay, so for astrology, so basically you can find the auspicious times, or like when you will have this an eclipse. Okay, so that kind of calculations you can do it easily with this kind of a device. So that is that was the main purpose of this one, and it was lost to the technology was kind of lost to time. Then like fast forward to 19th century, and then like Charles Babbage like invented the first like the analytical engine. So he built the analytical engine. So this is like widely regarded as the first modern computer, but it is the purpose of this computer was to calculate tables, okay, logarithmic tables, sine, cos, tan tables very quickly, okay. So and to make like to calculate accurate values for these. So why were the tables used again? So this sine, cos, tan tables and the logbooks like you used in A levels, so they were used in navigation. So they take it on their ships and then they use those tables to calculate, like first they look at the angle of the sun, and then using these tables, they are able to calculate the location where the ship is. Okay, the latitude and longitude. Okay, so this device was used to make those tables fast. Okay, so then from then we had ENIAC. Okay, so this is a computer like built by the US military in 1946. So through this time, like they are not discrete devices. Okay, through this time they have been improving the devices step by step. And by 1946, you have like one of these largest machines. This is 30 tons in weight. Okay, and you have 18,000 vacuum tubes. So it filled like an entire building. Okay, multiple rooms. And it was programmed by 6 women, actually. So the programming was done by switching the wires, cables, and it was used to calculate the missile paths. Okay, so you have done the projectile equations and everything in A levels. Okay, so they become more complicated when you have like a curved surface in like a curved surface of Earth. So you have like in such complicated situations, and when the target is big and things like that. So this machine was used to calculate such paths. Okay, so right. Then in 1958, okay, so around 1960s, used like the first integrated circuit. So there was like an engineer in like Texas Instruments who put multiple transistors together into one circuit. Okay, in one single die. Okay, it was quite big and kind of rugged. Okay, but they refined the technology and started using that in calculators and game ping pong machines and everything. Right. So from that, yes. So the commercial microcontroller was Intel 4004. Okay, so it was a 4-bit microcontroller with 2,000 transistors. Okay, so with 2,000 transistors in 1921, and then this was used in the calculators and pinball machines and everything. So now the electronic devices have started becoming small, widespread. People will start using them and everything. And then if you fast forward to today, we have the smartphone SoCs. Okay, so they are in every phone you have. Okay, so like if you have an Android phone, like it runs on Qualcomm device, or if you have an Apple phone, it runs on like the ARM architecture. It's built by Apple's contractors, right? So now this has 6.7 billion transistors in it. Okay, so the calculator. Okay, so if you take a calculator today, a modern calculator that you might use for like university or something, that has 350 times the power of the computers used to send man to the moon. Okay, so all those calculations in the the Apollo program was done by computers that were that weak. So now we have something within our hands which are like this. So if you have like a phone, then that is 120 million times more powerful. It can do that many more calculations in the same time. Okay, so if you have a phone, you can even download a horoscope app or like an astrology app or something if you believe in that, and you can have a star chart or something. So then you would have gone like a full circle of 2,200 years ago. What Greeks did, you are doing the same thing today. Okay, with your modern computers. Okay, so we have a full circle. Right. Now this is all good, but what about like the computing devices that we can actually use or we can like play with? Okay, so the smartphone computers, we can use them, but like we can't play with them. We can't like control different things. It's very integrated, right? So now you have like stuff like Raspberry Pis. So which is like a single board computer. So it's an ARM system on chip. And so you can run like a full operating system on that. And you can control robot arms, and you can you can build small systems to assist drones. So you can put a Raspberry Pi in a drone to do image processing and stuff like that. And you can do gardening, you can control like the water in your garden, and you can like control telescopes, okay, so to track stars, okay. So that kind of calculations you can those are some projects you can do with Raspberry Pi. So now it has become more democratized. So that means people like you and me, we can buy these things and we can build something more of it, okay. So that is the whole process of this, the whole objective of this workshop. So now that we have all this computing power in our hand, the question is what we are going to do with it. Okay, right. So if you are more interested about this, the history of the electronics, then I highly recommend this book. You can search for it like Idea Factory. It's like a really good book from that outlines the history of Bell Labs. Okay, so if you are electronic students, electronics and telecommunication students, ENTC, then like almost everything we learned in this 4 years of the syllabus was invented within one building. Okay, so that is the Bell Labs building. And so they, from starting from vacuum tubes to transistors to communication theory to everything. Okay, so most of the things were done there. So the history of how they developed it and like the problems they faced and how they solved everything. So it is like pretty interesting. So I highly recommend you to check the book out. Right. So even if you go to the bleeding edge, so the current technology, so now you have the chips which are made with 2 millimeters. Okay, so this is a picture like taken an X-ray picture of the latest chip, okay, which is 2 nanometer processor. So which means inside this the chips that are being made right now, the transistors, they have their widths are like about around 2 nanometers. So which means about 5 atoms. Okay, so you have like just 5 atoms you have between these, and that is a space you have for the like the transistors have become so small. Okay, so if you think about it, it's amazing because like those are they are machines. The transistors are machines. They do different things, right? Okay, so they are able to do like all these things very reliably and accurately at such a small size. Okay, we can't even comprehend that. Okay, so now let's go to the next part, which is okay. So if you haven't used like a microcontroller before, or like if you haven't heard of it before, then how do you like what's the idea behind it? So it's basically an electronic machine. Okay, you can think of it as a machine because it takes some inputs and it does some processing. Okay, so like and you can think of it as a small computer as well, a tiny, like you can put it on your fingertips. Okay, that kind of a tiny programmable computer. Okay, you can think of it that way. And it takes like very low power. It can run for days, okay, or months on battery. That's the idea. And it's very cheap. So and it can you can use it to automate tasks in your home. And you can, so at the end of this course, you will gain the enough knowledge to do these things. You can automate tasks in your home, for an example, like a doorbell or like gardening, things like that. Or else you can build, if you can come up with some ideas, some innovative ideas, you can build them and you can sell products. So I have some good friends who have come up with like some interesting ideas, and they have built and exported stuff on their own. Okay, so on their own, they have exported stuff to Malaysia. They have found clients in Malaysia. You can do these things and make money. Again, we can help our economy as well. Right. So the microcontroller is just, you give power and it takes a bunch of inputs and gives outputs. So how does it do does a transformation from input to output. So you basically program this microcontroller from your computer. Okay, so you can write some simple code. So we usually use C++, which you will be learning. And using that code, you are telling how to take these inputs and how to do the transformation into the output you. Okay, now what are these inputs and outputs? So if we look at it, that depends on different applications. Okay, if you take your first application, for an example, now if you want to adjust your fan speed automatically, okay, based on the temperature. Okay, so which means like if it is too hot in your room, then you want the fan in your room to speed up. And if it is too cold, you want it to slow down. Okay, so for that, the input will be a temperature, so temperature sensor, and the output will be a speed controller. So similarly, you can water plants in your garden based on how wet the soil is. Okay, so if it is soil is dry, then you start pouring water. So how do you know that? For that, you use the humidity sensor and to the input. And the output will be, you can connect it to a relay switch, which controls the solenoid valve. You can also like build a simple system to fill your water tank automatically based on your water level. So which means if your water tank is empty, your motor will start and you can automatically fill it. Madhu, can you mute your, yeah, okay, thank you. So you can do that. And how do you do this? For the input, you need a water level sensor, and the output will be passed through a relay switch to control the motor, right? So similarly, you can have like Vesak decorations you might have seen. There are like beautiful lighting patterns. Okay, so those are also controlled by a microcontroller. So the input, you can have like a push button to change between different patterns. And the output, you can have a set of transistors to amplify the current and give it to lights. Similarly, you can have a line following robot. The input will be the line sensor, so IR sensor, and the output will be motor controller controlling the motors. So like that, you can have like a voice control AI system. For example, you can say switch on the lights, and the lights in your house will switch on automatically. So for that, the input has to be microphones, and the output you can do whatever you want. So if it is lights, you can control the lights and things like that. You can have like a self-driving car using the vision. So for that, the input will be the camera, okay, camera input, and the output will be motor controller controlling the motor. So can you see like a common pattern here? That means the output from this microcontroller, we don't directly connect it to the device. Okay, so for an example, we don't connect the output directly to a motor. Why? Because the microcontroller is like a low power device. Okay, it works with very low currents and low voltages in general. Okay, so it doesn't have the ability to drive a motor or like switch on like the large set of lights. Okay, so for that, what we do is we use like these amplifiers. You can have like a relay switch, or else a transistor amplifier, or like a motor controller, which is a set of amplifiers. So which will amplify your signal and will control whatever you want to do. Okay, so we'll be in the project, we'll be doing this. So you'll be building like an entire system. So you will know how to take these sensors, how to connect them to a microcontroller, then what kind of amplifiers to use, and how do you connect that to the stuff that you want to control. Then how to write this code which can do this input to output transmission. Okay, so we'll be looking at all of that. Then we have okay, a brief overview of programming. So After you connect all these things, you have to program. So you have to tell how to convert those inputs into output, right? So for that, you come up with some logic. Okay, so here the simplest logic is it's a garden watering system. Okay, so you are checking the humidity, and you are checking if the humidity is greater than some threshold. Okay, so or else if the humidity is less than some threshold, and if it is, then you output 5 volts. If not, you output 0 volt. So this is the idea. You are just checking the humidity. Based on that, you are like changing the output voltage. And for that, you can write a simple C++ code like this. And then in Arduino, and after you do that, you compile it. And when you compile it, you get assembly code like this. So this is the actual assembly code that runs in your microcontroller. Okay, so this is called low-level code. And whatever you write in C++ is a high-level code. Okay, so this is how programming works. And then this assembly can be programmed into your particular microcontroller by using the software that they gave, as well as, so it's called the tool chain. So using that, you can upload this code into as a machine code into your microprocessor, and then it starts working. So that is how you come up with some idea, come up with some algorithm, and you do this. So we'll be training you on that as well. So the next biggest problem in embedded design is choosing the right hardware. Okay, so you have like thousands of different varieties of microcontrollers, hundreds of thousands out there. Okay, so for an example, you have like these are two of the popular ones, Mega 328P, which is there in the general Arduino, and you have one called a tiny like 85. So you can see the memories are different, the RAMs are different, and you have the flash memory, like number of pins are different, is 32 and 8, and analog pins 6 and this one, and the price is also different. We have things like that. So this way you have like thousands of different chips, and all of them are like completely different. So then like we will tell you how to pick like the right chips to do the right task. Okay, it can be quite daunting. So that way you can figure that out as well. So this was the situation like I think about say 15 years ago. Okay, the electronics, the situation was something like this. That is, you have to go through all these manuals and everything, and you have to find a chip, and then you have to set up all these things yourself in your computer, and then you have to program like in C, like in assembly or things like that. And it is you have to build your own PCBs like before you can do anything. Okay, so that way it is like it was super difficult. Okay, but then with Arduino, the field has become democratized. So which means anybody can buy this and start working with this immediately. Okay, so you can just have a Arduino lying around. You can just connect all these things. You have all different kind of sensors. You can connect them. You can write some code very quickly, and within like 10-15 minutes, you can test an idea. Okay, so you can test an idea, test a prototype. Okay, so this has made things like very easy for everybody. But these are prototypes, so which means like you are testing out an idea. Later on, if you are going to sell stuff, you are not going to use Arduino. Okay, you'll be making your own PCB. You'll be doing the same thing again, but with only the circuit that you want, only the microcontroller, only this one in a PCB. So we'll be teaching you that as well. Okay, in this course. So you have like so this is like a common, like an Arduino. You have like different parts. Yeah. So this way you have like multiple development boards, and even Arduino, you have like Arduino Uno, Nano, and then you have like a different architecture. You have STM32. Then you have something called PyBoard, which uses Python. This is C++ that uses Python. So like that, you have different development boards. So previously we looked at different microcontrollers. Now we are looking at different development groups. Okay. So this black part is a microcontroller, and everything around is a development. So having a development board is very easy. So it will help you to connect things very quickly and do stuff. So that way, like you have a lot of options there as well, and they are used for all different purposes, and we'll be outlining that as well. Okay. So the next one is like, so after you learn like these things, so one thing we'll touch upon is the product development. Okay. So which will be the next part of this the course as well. So we'll dive deep into it. But here I will give like a quick kind of overview on that. So we see that in Sri Lanka, you have a lot of inventions and innovations. Okay. So every time you go to an exhibition, you see people coming up with ideas and they have like things that are working. Okay. So once in a while, you see the news that people are like, somebody changed, like somebody invented a three-wheeler that can go, or some sort of a device that can go uphill or like something like that. Okay. So all of them, and they make headlines. Okay. But the problem is none of them come to market. Okay. Only very few come to market. There are like actually some startups, several startups which are successful. Okay. We have Pygmy. Okay. And like so companies like that are successful. But other than that, a lot of these things we see in the exhibitions don't come to market. They don't succeed. Why? So for that, we need to understand the difference between a prototype and the product. So what you see everywhere and what you see in TV. Okay, so in exhibitions, like all the the stuff they tell and as an invention, that's a prototype. Okay, so it is relatively quite easy to make one device, one working device. That's a prototype. But it is very hard to make like 1,000 devices to sell, to mass manufacture and sell things. Okay, so here's a quote by Elon Musk. So he's getting a lot of hate these days, but still he pulled so this was actually posted about Tesla, right? So in 2000, I think around 2018, Tesla was going through a really hard time. So they had built one car, but then what to make it into a million cars and sell it around the world, they have to build factories and everything. Okay, so that was like a really hard process. It almost destroyed their company. So you have that kind of issues, and it's the same reason why most of the stuff we see don't come to market. Okay, so people are good at doing prototypes, but not products. So we will see what a product development is. Okay, so before that, let's look at the prototype. So if you do a prototype is what you have using Arduino boards or using Raspberry Pis. It is each of these unit cost is quite high, and the lifetime is quite low. That means you don't look into what the temperature control or these things, right? So temperature, weathering, so you don't consider those. You just want to check if your idea works. Okay, that is the prototype. So you have multiple ideas, multiple types, like proof of concept, working prototype, visual prototype, so things like that. So you do all these things one after the other before you go into mass production. Okay, so what is mass production? In mass production, you build something like, say, 1,000 or 400 or 1,000 units. So before that, you want to make sure everything works and you don't have any mistakes. So that is why you build these prototypes again and again. But you cannot sell a prototype and you can't make money on it. Okay, so you are doing basically research and development in this step, right? So when you actually go for product development, you have to consider a lot of different things. So mainly there are two different types of product development. So you have one is user driven and design driven. So we'll look at these things deeper in the future. So in the next course. So the main idea is the design driven development is something like Apple. Okay, so you have when Apple introduced the iPhone, there was no market for smartphones. Okay, so they came up with the idea and they thought, okay, people will need this, but nobody knew that they need it. Okay, so if you go around people in 2007 and if you ask people, do you want a phone with a touch screen without buttons? Okay, I'm pretty sure everybody would have said no. Why? Because everybody was used to buttons and everything, so they can't even think about it. So then like Apple released this and it became a success. So that is called a design-driven development. Okay, and that is quite risky. Okay, so which means like in our stage, like we don't do that. It is too risky to do it in our stage. So what we generally do is user-driven development. So user-driven means, let's say you have an idea, like I want to like sell this product, some sort of a gardening system or something. Okay, then the question is like you have to find out who is your market. Okay, you have to identify stakeholders, who are the people who want these things. Then you have to go and talk to them and find out if they really need it. Okay, so because sometimes we might think they need it, but they may not. Okay, so you have to figure that out. And then you have to select the requirements. Then you have to make prototypes. You have to give them the prototypes. Okay, and then they will tell, okay, like this is too big. Okay, I can do this part myself, but I want something else. Okay, so like that, you have to talk to the users a lot. You have to collect surveys, and finally, you have to make your design. So that is the user-driven development. Okay. So the next part is first part of prototype. So before you even go into building like a full-scale prototype, what you can do is simulation. Okay. So these are like different types of simulations. So we will be following this methodology throughout this course as well. So the very first thing we'll be building is using an online simulator. Okay. So we will write our code because you can test it very quickly. So you don't have to upload it offline, you don't have to put wires together, you don't have to do anything. You just open a browser, you can connect an Arduino and you can put some virtual wires, you write some code and you can check whether the thing works. Okay, so that's like really fast. And that is the very first step. And once you get that logic correct, then we will go on and build the circuit in real world. Then we go on and build it in as a PCB, and that way we will progress. Right. So this is for analog circuits. Then you have like for some intricate analog circuits, you have PSpice. And then for mechanical designs like this, you have SolidWorks. And then for control systems, MATLAB. For robotics, you have like ROS, okay, to check like complex robots and stuff. Then digital circuits, like chip design. So this is basically what I do. So you can check all this about you do it in this kind of simulators. So simulation is very important, and it is like the very first step before you before doing anything else. Okay, to make sure your idea works. Okay, so let's go for a quick story to tell about like some ideas, some fundamental ideas in engineering. Okay, and how it relates to product development. So these are two of the most iconic aircrafts ever built. Okay, so we have first one is a Nighthawk, and the second one is a Blackbird. Okay, so these were built by Lockheed Martin. So it's an American company. It was built for America during the after the Second World War, for the Cold War, during the Cold War time. So America and Russia were in Cold War, so they wanted to spy on each other. So in America, like the government, they give contracts to these companies. So the first one, like they gave these contracts to Lockheed Martin, and the Lockheed like what they did was they formed a small team. Okay, so the problem with these aircrafts was there was no technology at that time to build them. So which means you have to build everything from scratch. You have to do like a lot of work, and it is very risky, right? So they formed like a very small team of very talented engineers. So they are called the Skunkworks. Okay, and so what I'm going to the stories I'm going to summarize here are from this link. Okay, I will give these slides. Just check it out. It is from a YouTube video. So which is actually a really good, interesting story of the engineering process, right? So if you take the first aircraft here, it's a Nighthawk. It's named Nighthawk. The idea of this aircraft is basically it has to be stealthy. Okay, which means it should not be caught in radar. So that is the basic idea. Okay, so it has to be as stealthy as possible, right? But the problem was what? So when they started designing this one, like it was in 1981. So in those times, the computers were not powerful. So you saw the photos. So they were so huge. So in 1960s, they were huge. In 1980s, you had like the powerful computers were too big and slow. So you can't run like complicated software. So their computers could only simulate flat surfaces. Okay. So what they decided was, now the simulation is very important. So that's how we iterate. So what we are going to do is we are going to make a plane full of flat surfaces. Okay. So and they ended up making this one, like the plane that looks like a paper plane, like a origami. And when they finally built it, and like when they took it to the testing pad, they found, and so you put this whole plane on a pole, okay, on a stick, and then they were measuring the radar frequency from far away. And so after all this design, then they found like there's a problem with the radar, and you could not see the aircraft at all. Okay, so the design was so good, the aircraft like completely vanished in radar signature. Okay, so it was like a marvel design, and even now, so from 1981, even now, like 40 years, this plane they have been using this all this time. It has been only shot once, so by a mistake. So other than that, it has never been identified. So yeah, so like that, the second one you have is a Blackbird. Okay, so this was like mainly built in simulation. Okay, so with the power of simulation back in the day, like 40 years ago. And the second one is a Blackbird, and the design of Blackbird like gives a very important foundational lesson on engineering. Okay, so the whole idea of Blackbird was it has to be the fastest aircraft ever built, and it has to fly the highest. Okay, so yeah, so the fastest aircraft, and it has to fly the highest. Okay, so that was the requirements given, and they started building it, and they found, okay, so there were like a lot of problems. Okay, so you have to minimize the weight to make it fly faster and higher. So how do you minimize the weight? Okay, so this team of engineers, they came up with the designs, and what they built finally, okay, had a bunch of problems. So for an example, like when this plane, so it is legendary, it's even there right now. So when this plane is in the ground, so when you fill it with fuel, what happens is the fuel starts leaking out of the plane. Okay, and that is a design choice. Okay, so they designed it that way. Why? The reason is when this plane goes to the full height and goes to the full speed, at that height in the atmosphere, it starts heating up a lot and it starts expanding. Okay, so which means like the panels will expand and they will fit together, and they will, at that point, it will stop leaking. So which means the ground, the panels don't align and it has to keep leaking. And similarly, it doesn't have a landing gear. It can't start its own engine. Okay, so it is very counterintuitive. So if you look at these two designs, it was very counterintuitive, and they don't have a lot of features of you find in good aircrafts. Okay, but this plane, even after like 40 years now, is the fastest aircraft in the world. Okay, SR-70. So SR-71, Blackbird. So yeah, so they built it in 143 days, and it serves for 40 years. So the lesson here is trade-offs. That means if you want to build something the fastest, then you have to figure out what is not important. Okay, so for an example, here, like it is not important for this plane to start on its own. Okay, so that is what other planes do. But this plane, like you can remove it. So like that, you keep on removing unnecessary parts until you optimize for the core goal. Okay, and the same thing happens in product development as well. So when you are coming up with the design, you have to make sure, if you are selecting a microcontroller, you have to make sure you are choosing the cheapest, the smallest, and the most available microcontroller possible. Okay, for your particular task. And you have to remove all the other features. Like, okay, over here, if you are like talking to some users, you have to remove the features not needed. So that way you can optimize and you can come up with a final design. Right. So for prototype development, we mainly use Arduino and like Raspberry Pi. So this way you can try different things, and like you can build your products quite fast. So this is after simulation, right? But the problem is this is not suitable for the final product. Why? Because you can't mass manufacture. Okay, so you can't put an Arduino inside a device that you are going to sell for like 1,000 people or 100 people. Okay, and it may not meet the requirements. Why? It is not waterproof. It is not dust proof. The dust may go into these small holes and everything. Okay, and the lifetime will not be perfect, and it has reliability issues, things like that. Okay, and it has a high unit price. You can do it way cheaper if you make an actual product. Okay, so which means the prototypes should not be made in sold as products, right? So these are the development board based prototypes. You can have like small robots and things like that. So this is the vision based control robot. Okay, you can have a camera. Based on the camera, it navigates itself, right? Okay, so what is the final prototype? So the final prototype is something that resembles the actual device. Okay, so for this you need to have an actual PCB, something that looks like this. Okay, so you will be using that microcontroller from your which you have chosen, and then like you will be using only the circuits that you want. Okay, only the sensors you want, only circuit you want in the smallest size possible. Okay, so you'll be routing things like this, and then you will be making them into a full product. Okay, you'll be making a PCB enclosure, and you will be making all these things. So you have to, in the final prototype, you also have to look into like ease of assembly. So it should be able to, you should be able to assemble it easily, because this is going to be the actual thing that you're going to make later on. Okay, so you have like a lot of things, and this will be covered in the second course. Okay, so the advanced ideas of like a product design. And this is the manufacturing processes. So you have like, you build things like in different ways. So this is a screen printing method. We will talk about this later. Right. So for the final few slides, I will just introduce some of the designs, embedded designs that we have, so our friends have done. So this is Kitman's final year project. So this is basically PCB. Okay, so this is a PCB, but not a regular PCB. Okay, so this has to be, so the idea of this is basically it measures the electric signals from your hand, from your muscles. Okay, and based on that, it predicts what kind of gestures that you are doing. Okay, so they design the sensors themselves, and they circuit themselves, and this has to be designed in a way that you have to design it so that noise is so low and everything. So these biomechanical circuits, these bioelectrical circuits have to be designed for low noise and high sensitivity, so these kind of things. So it's way harder than a regular embedded system. Okay, so they have you can check out their thesis and their stuff in this blog, and this is quite inspiring. Right. So this is another project by Kitman. This is called a micro mouse. So micro mouse is something like a simple robot, a wall following robot or something, but it is not so simple because it has to the whole idea is how fast you finish the whole circuit, right? So how fast you finish the task. So generally they do it in within seconds. You can just Google micro mouse. It's very popular competition around the world. So to do things so fast and so like so accurately, you need to build like very compact, very sophisticated circuits. Okay, so this is the PCB is being built for that. Right. So this is my own final year project, which is a vision-based traffic control. Okay. So for the final year project, what we built was a system like this. So the idea is like you can so you have in Sri Lanka, you have these traffic lights, and these traffic lights are statically controlled, which means there's a timer to tell after 10 seconds, you turn to red, after 10 seconds, you turn to green, like that. So which is not very optimal. So our solution was to build a vision-based system where you place cameras on all 4 sides, and the cameras give you a video feed like this, and in the video feed, we process the video feed in an embedded system. Okay, so in a small system over here, you process it, and what kind of processing do? We take this image and we pass it through a convolutional neural network, an AI. Okay, so the CNN, and through that we detect these vehicles. So this is a 3-wheeler, this is a car, this is a truck. We detect the vehicles, then we track the vehicles, and then based on that, we adjust the green times. Okay, we find how many vehicles are flowing in each way, and based on that, we have an algorithm to manually change the green times. So for this, we designed our own chip. Okay, we designed our own circuit to do this thing. So this is one of the, like, you can consider it as an embedded as well. So this is like a robot built by Ray. So and his team. So it's a 4-legged robot. Okay, why? Because it can go in uneven terrain. Okay, so in the grass and in forest and everything. So in sandy, this one. So they have like a really good mechanism as well, and it has a certain advantages. So this is an elephant collar project, which was done by some of our batchmates like Tamilu. So this is like attached to elephants. So it's an IoT device, like in a low power device. So it runs for like several, like 1 or 2 years, and it tracks the positions of the elephants. So we can minimize human-elephant conflict. Okay, so we can prevent them coming into the villages, and we can prevent the crops being destroyed and everything. So battery life is 3 years. Right. So I would like to end this presentation with a few people like who are doing like great things. So yeah. So you can go to the LinkedIn profiles, you can see. So this is to what inspire you. Okay, so the whole purpose of this is to inspire you. So the thing is, you have like, there are a lot of Sri Lankans, okay, a lot of people who have like studied just like you. Okay, so I'm pretty sure they started their like education like as an undergrad without knowing any of this. Okay, so most of the people, they start like without knowing microcontrollers or anything, and now on the way they learned, they started building their own projects. Okay, they got so good at it, and like they got hired in big companies. Okay, so he's now this like Atlanta is there in Apple, and he actually has like a lot of patents. Okay, yeah, so you can go through his profile. Okay, so Atlanta, he has a lot of patents on embedded system related things. Okay, so this way you can check out their profiles. Okay, so there are a lot of people every year. You have like 10-15 people who are like going to these big companies, and even in Sri Lanka, inside Sri Lanka itself, you have people who are starting good startups. For example, Magic Bit. So they are doing like really good work. So that way, like there are people who are using these skills to make money and to improve the economy and to help other people as well. Okay, so that way, like the skills you are going to learn in this course, they are going to be really useful. So you can do whatever you want with them. You can build your own things, you can sell your own things. And one day you'll be able to go to places like this, okay, to have a very successful company here in Sri Lanka. So all of that will be possible. Okay. So yeah, now thank you so much. I will be going through the questions. If you have any questions on the stuff I talked about. Okay, so that is it. If you have any questions, you can ask. So about the course, or it's like about whatever we discussed here, the projects we have done, to any possible job aspects, like job future in Sri Lanka or like abroad. Yeah.
Thank you, Abba, for that presentation. I'm looking at the Zoom chat also. Did not get any questions.
Yeah.
If you have something on Slido, we can also check. I'll do that. Let's give people a few minutes if they would like to clarify something about the session done by Abba or the previous discussions that we had. Anything you would like to get clarified, now is the time. Otherwise, we'll be concluding today's session in a few minutes. I think we are not okay. You have a question?
Yeah.
Do we cover the phases involved in mass production for a product? Not in this course. No. We are planning to do that in the product design course. That will happen in the future. Cool. Yeah, I think another question is Altium free to use? So at University of Moratuwa, we can get the license through the email that we get from the university. For others, the free version, those who are familiar, very much familiar with Altium, can one of you comment, please? The Altium circuit maker, to the best of my knowledge, that is, you can get it for free. If the other instructors have, those who have used it very recently, can comment on that, I think.
I think so. It depends on the university, but if someone's interested, they offer a 30-day trial for Altium. Otherwise, you have to purchase Altium to use it.
Even the circuit maker version,
it's free.
It's free, right? Circuit maker is typically free. Yeah. yeah, the other more comprehensive design suites will have to be paid, of course. But the software that we're using in this course is free. Please correct me if I'm wrong.
That's true.
Right. Hope that clarifies. Right, I think we are not getting any other questions. It's been about 3.5 hours now. We are glad to see many of you tuning in today. We actually did not expect this many people to take part. At some point, it was around 110 people, and currently there's half of it. So that's, I think, a huge achievement. So it's really good to see all of you joining here today, and we expect to see most of you from day 2 onwards as well. Please follow the instructions on the web page, and if you would like to continue with the course from day 2 onwards, we've already given you instructions, so you know what to do. Thank you for the presentation, Abba. I think that laid a very good foundation to what we will touch upon from day 2 onwards. I think people have the background now, and now we can get our hands dirty and get into the thing and do the programming and develop something. So which is what we will do starting next Saturday.
Yeah, Dr. Charles, on my personal behalf also, I'd like to thank you, Mr. Abarajithan, and all who are involved, and also the participants also. And I encourage them to continue with the course and learn this. Thank you very much.
Thank you very much, sir. I know that you were in a very tough schedule today morning, traveling here and there, and then you joined with us for 3.5 hours. Really appreciate that and the encouragement, and for your the presentation and the kind words also. Thank you very much. Okay, so with that, let's conclude the first day of the microcontroller-based embedded systems course. We look forward to seeing you from day 2 onwards, and hopefully meet you in person. Not hopefully, for sure. In the near future, we'll meet in person. So it'd be quite great, because we've all been at home for a long period of time, and now interacting with people in person, it's always good. So we'll facilitate that also through the course. Thank you for tuning in today. We look forward to having you from day 2 onwards. Have a good rest of your weekend and a good week ahead. Thank you.
Thank you.